I do
Okay.
have one question for you.
Yes.
So I noticed on the book it has like T815.
That is the question in the question pool. That's the identifier for the question in the pool.
So like on the technician study guide, are they matching basically?
Yep. Because every question, actually, this book is great because every single question in the pool is in the book. They are
Okay.
all there. And if you
Has
go
it,
to take practice tests, the practice test will actually say, like, question T5C28.
Yeah.
I mean, there are no surprises. You
Okay.
can't have surprises.
This is
what,
interesting because this is the way I do my test for my kids in science.
Mm-hmm.
I give them a pool of questions. We go over every single one of them, and then I pull from those questions for the test.
Yep. And
well,
actually, the way this works is that you will basically be generated okay, so each section has a certain number of questions that have to show up on the exam by the way that the exams are written, right? That's when the volunteer examiner coordinators, the VECs, meet with the FCC and say, this is what we propose for the exam questions. Because to be honest, the FCC wants no part of this. The reason the FCC wants no part of this is because they get how much money for examining people? Zero. So they want no part of this process. So they have delegated it to these 14 volunteer examiner coordinators that get together and have a meeting, come up with the pool, propose it to the FCC, and they either approve it or not, or say we need to change something. More often than not, they're just like, yeah, you know what you're doing. So the question pool then becomes, then becomes the rules essentially for giving exams. And it's such that one question from this section, two questions from this section, one question from this section, two questions from this section, which is why I can comfortably say, okay, you're not good at math. The most you'll ever see is 3 or 4 math questions because that's the way that's the way every exam is written. And the website that everybody uses randomly generates an exam based on those rules, a unique exam for every person. So if you say, oh, I got a really hard exam, well, okay, it's not really hard. It was just hard for you on that day because you've seen all the questions. They're all public domain. So
so
yes, it's $10 to take the exam if you go through Anchorage. If you go through other groups, it can be anywhere between $0 and $15. The FCC charges $35 to process a license. If you're under the age of, if you're, I believe, 18 and under, and you take your exam within the ARRL VEC, the ARRL is the National Organization for Amateur Radio that also runs a large volunteer examiner coordinator crew. Um, you'll get basically you can apply for a $35 stipend essentially, basically where you send in the $35 to the FCC and you keep the receipt and then send it to the ARL and they will send you a check for $35. So that
so
is a yes.
Scott, what does it
Mhm.
mean on when you look at the practice test, and then at the end you're looking at your results in that plot, and it says T1,
T1
this
is section 1.
5 question.
Yep.
So section 1 of what?
Section 1 of the question pool. If you look at
Okay,
the
so it
question
means,
pool,
okay, but that's not tied to some category of something?
it's tied to
It's
the
just,
category of question.
so it's just random to me. It means nothing to me.
Well, it can mean something to you. Um, let's see,
Because I missed a
technician.
lot of T1 and
Th-
one only of the others.
Okay, well then you need to focus on the T1 questions.
Right.
Uh, whatever those questions are. So
Okay.
let's see.
So if you do ham.org and I look at the T1, which I did, there's a like bunch of questions. That's what I need to be going through.
Those are the ones you need to focus on.
Okay,
Let's
I
see
got
what
it.
And my understanding, Scott, is that the question pool is the entire question pool, meaning the right answers and the wrong answers in that pool are also on the test.
Yep. There are no surprises.
So if you get familiar with like the T1 section, you're not going to have any surprises there. That all the answers are going to be the same.
If you've seen
So
all the questions with all the answers, that's what you get. Okay, so like here's the layout of the exam. Sub element T1, commission's rules. There's
Yeah.
the sections and subsections. Operating procedures is 2, radio wave propagation is 3, amateur radio practices is 4, and so on and so forth, all the way up to number 0, which is safety.
Yeah, so T5 was tough for me. What I've been doing is just going through it and so I can recognize what the right ones look like.
T5 is electrical principles.
Yes.
Yep.
So I've just been memorizing the right answers.
Yep. That's what my kids did. That's what my wife did. Honestly, to be honest, that for some exams, that's what I did when I was a kid. All right, here we go. We are into amateur radio signals. Okay, so what I'm going to do is I'm going to introduce a concept that we sort of touched on yesterday. If we have a graph that looks like this with a little letter T, that is a time-based graph. That goes like this. That means that in a period of time, we can look and see what our value is at any given time. That is known as the time domain. Now, we can also do through something called a Fourier transform. Has anyone ever heard of a Fourier transform? You don't have to do it, thankfully.
No.
Essentially, what a Fourier transform is it takes this signal, for instance, and says, what are the components of frequency that show up in there? So if I have a frequency that looks like this, a sine wave that has a frequency of 1 kilohertz, which is 1,000 of these per second, and I translate this to a frequency domain representation. Frequency domain is how often something happens per frequency. So I'd have, this is in hertz. This is 0 hertz up to, let's say, 3,000 hertz. I had a frequency of 1,000 hertz. I would have a spike right here at a frequency of 1,000 hertz, because in my time graph, it looked like this, and I had a frequency of 1,000 hertz. So essentially what this is a pictorial representation of that. If I also had another one that looked like this, that was 2,200 hertz, but it's a lesser amplitude, I would have this. It would also show up right there at 2,200 hertz. So this is a spectral display. It's a frequency display of what is happening in time. And it's a different way of looking at things. You can take a time domain. This is time domain. This is frequency domain. And you can basically transform it from time to frequency and from frequency to time. Now, one thing that's really useful here is in visualization. If I were to take the time domain something, right, this graph up at the top, how would I filter that? I have no idea, right? But if I can look at the bottom one and say, I have this frequency chart, how do I filter it? Well, I can do this. Let's say I want that one, but I don't want the other one. Well, this is called a bandpass filter, and I can build that, and I can center it at that frequency by using these and these. So frequency domain representation is extremely powerful, and it gives us an easier visualization of what's actually happening in the frequency space. It's also really important to understand when we start looking at how a signal is modified to do something. So we have something called a carrier frequency. This is our marker that we're going to modify. And let's say that in this case, this is 3.00 megahertz. So what would you say the frequency components are of this very pure sine wave? How many components are there?
One.
There's one. That's right. And it's exactly at 3 megahertz. Now, the question is, what do you know by looking at that signal? What do you know about it? You know it's there, right? Okay, well, that's information. But it's only information if sometimes what happens to it? If sometimes it's not there. If it's always there, that doesn't tell you anything. If it's there sometimes and not there other times, that actually tells you information. If it's there, let's say you have a signal that looks like this. And then for a half a second, that goes away. And there's another signal that is now over here. And then that signal goes away. And it comes back over to this frequency. Well, so for a little while, it was over here. It shifted. This is known as frequency shift keying. If those signals are related, the fact that they move back and forth tells you something about the signal, right? Modulation is the act of taking a signal, a wave, and doing something with it so you can put information on it. So that information might be as simple as doing Morse code. If I were to look at Morse code in a period of time, I would have this. Here's a signal, and then it goes away. And here's a signal, and then it goes away. This is in the time domain. So what is this telling me? This is telling me on, and this is an off. And this is an on, and this is an off. This is a very simple method of modulation. This is what we use for Morse code. It's also known as on-off keying. Now, instead of switching something off, we could actually, during that time, do this with it. Change the color so it's easier to see. What have I done right there? What have I changed?
Frequency.
The frequency. I changed the frequency. Instead of on-off keying, this is known as frequency shift keying. If I were to continually do this kind of modulation, if I were to, instead of just going with two separate ones, I could actually continually change my frequency based on what was happening. This would be called FM. Anyone know what FM is?
Frequency modulation.
Frequency modulation. That's right. Okay. I could also, if I wanted to, do something like this, where I always had the same frequency, but I could do this with it. What am I doing there?
Amplitude modulation.
That is called amplitude modulation. Modulation is changing a very boring signal, which just goes on forever, to make it convey information. This is known as the envelope of an amplitude modulated signal. And if I could actually kind of like flatten all this out on the inside, this envelope actually is a picture of my waveform, which is usually my voice or something like that. So now what we're going to do is take that exact same thing and we're going to look at it in the frequency spectrum. So here's our center frequency or carrier frequency. And FM continually does this. It spreads that signal out over a whole bunch of different frequencies. This is FM. What do you notice at all those different frequencies? What doesn't change?
Amplitude.
The amplitude. It does not change. The only thing is that it sweeps through a different range of frequencies. Now, I could also look at a frequency representation of an amplitude modulated signal. You might notice something that looks a little bit different. Here's our carrier frequency, and here's an amplitude modulated signal. What do you notice about that now? what happens as you change frequency? What happens to the amplitude? Well, it's big in the middle
It goes away.
and it goes down.
Dies,
Yeah.
it gets weak.
Yes. Okay. Now there is something else also about amplitude modulation. It has a carrier frequency. It also has an upper sideband and a lower sideband. And if I've drawn this correctly, what do you notice about the upper and lower sideband? Assuming I've drawn it correctly, what do you notice about that? I might need to touch that up a little bit.
They mirror each other.
They mirror each other. That's right. Well, if they mirror each other, do you need them both to get to know what information is there?
No.
And the answer is no. So you pick your upper or lower sideband and you filter out the one that you don't want when you're generating the signal, and then you don't have to send them both. So now your bandwidth, instead of being this big, is now only half of that. Well, if you save bandwidth, that means more signals can exist at the same time without interfering with each other when you're actually going to receive it. What it also means is that if I have a certain amount of power, a certain amount of power available to me in my transmitter, that would normally be used to fill this entire signal to a certain height with a certain amount of power, I would have to fill this entire space. But if I only have half of it, I only have to fill half the space. If I only have to fill half the space, but I have the same amount of power, I can actually fill it deeper. I can actually fill it up higher, make a bigger copy of it. What that means is that the amount of power that I can dump in at each frequency goes up, which means I can put more power into the signal that is of interest to me. The other thing we can do is this carrier signal, I can make this actually go away because it doesn't have any information other than where the signal starts. Well, if I'm creative and I tune around on a radio and I hear, and I can do that, I can actually create my own carrier in the receiver, replacing the one that was originally there that we took away. This actually uses up a lot of power to transmit a carrier signal. So by just transmitting the sideband itself, I can become about 70% more efficient. And that is why people use single sideband, because it's a lot more efficient. A typical single sideband signal is about 3 kilohertz wide. If you were to filter for it, it would be about 2.4 kilohertz wide. If we were to look at AM, AM is about 6 kilohertz wide. And you also have the power in the carrier signal that you're transmitting. The reason we don't use FM in certain places is because the signal, an FM signal, is about 15 kilohertz wide. So why would we choose one over the other? We look at efficiency. We look at spectrum use. This is another something that we have to mention, which is how spectrum gets used. Spectrum is a limited resource. Let's say we're looking at a band where we have on the 20 meter band 14.000 to 14.350. So this is actually from bottom to top 350 kilohertz. And an FM signal takes up 15 kilohertz. If an FM signal takes up 15 kilohertz and the whole band is only 350 wide, we can only put about 22 of those signals on that entire band. So let's instead look at a sideband signal. I'm going to go 3 kilohertz. And all of a sudden, we have 3 kilohertz in 350. We can put over 100 of them on there. Let's pick a narrower signal. We're going to go with Morse code. Morse code actually fills up a space of about 150 hertz, or 0.150 kilohertz. So we can fit something on the order of, let's see, that would be about 2,000 of those. on that in that same band. If we were to go with something even narrower, like PSK 31, which has a frequency of 31 hertz, 31 hertz is 0.031 kilohertz. This is a digital mode, again called PSK 31. And we can fit about 10,000 of those signals on that band. So that's why we use different modulation techniques. Now, what you lose when you go to a narrower bandwidth is you lose some fidelity. Does it matter? It depends. If you're trying to do high quality audio, yes, it matters. But if you're trying to do a digital signal and get information from you to somebody else, it probably doesn't matter. So the more efficient we are as far as using our bandwidth, the better off everybody is. So what I have here is, and I hope everybody can see. Can everybody see that?
You don't have your screen up.
Okay. Oh, I didn't finish hitting share. Darn it. There we go. Can everybody see?
Yep.
And now can everybody hear that?
Your STR.
Yes, this is an SDR, which is software defined receiver. And we are actually looking at, on the left-hand side, 14 kilohertz, or sorry, 14 megahertz. And over here, we are out to 14,350. This is the entire 20 meter band. And notice what you see here. Over here, we have wide signals. Those are single sideband. What happens when we tune off the frequency? What happens to the voice? What do you guys
Goes
hear?
away.
Distort.
Distorted because the frequencies are wrong. Same thing if we go the other way. That line right there on my little passband, that is the center, that is the carrier frequency. If we put it in the right place, here's another one. If we put it in the right place, we will actually hear audio. Okay, any idea what this is?
Data.
That's data. Yep, that's what data sounds like. That's frequency shift keying. Notice the tones are shifting all over the place. The tones moving all over the place represent a sequence which relates to data. Over here, this is a very narrow bandwidth mode called FT8. And
Low band TV.
Yeah, every one of those little vertical stripes in this window here is a separate signal. These are incredibly narrow signals, and they're used to transmit just a little bit of data. But we can put a lot of them. This little passband, the yellow window, is the same width as one single sideband signal, and there are about 40 people having conversations in that window. This right here, this is phase shift keying. Notice it looks like an almost vertical stripe. Very narrow bandwidth. That's keyboard to keyboard. Anyone know what this is?
Morse code.
Morse code.
Okay, so here's a question for you. If Morse code is just represented by a signal turning on and off, this clearly does not have zero bandwidth, does it? You can see on the chart that it actually goes from narrow to wide. Like if we look at this one over here, notice it goes from narrow to wider. Why is that? If it's just one tone that's being switched on and off. Anyone have a guess for this one?
Does it have to do with time?
Nope. And the faster the signal is, the faster it switches on and off, the wider it gets. And that is because of a fundamental fact of something called the Shannon sampling theorem and information theory, which is that if you modulates something, if it carries information, it must take up bandwidth. Even though it's just do, 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 which is the same tone, right? That doesn't change that doesn't change pitch. It doesn't change tone. It doesn't change its location. The act of turning it on and off generates the use of bandwidth. So Morse code is known as CW. That's about 150 hertz. A common filter that we use for this is 500 hertz wide. So here's our signal and here's our filter around it. That allows us to block out adjacent channel noise. Single sideband is about 3000 hertz wide. That's typical human speech on communications. We very often use a 2400 hertz filter, and we basically say that we're going to ignore the very bottom and very top, and we're going to catch most of the signal, and then we're going to ignore everything outside.
Why not just use a 3000 hertz filter?
Because sometimes bands get really crowded and signals start to overlap at the edges just because there's not as much space available. So I mean, you can certainly use a 3 kilohertz wide filter. AM takes up 6000 hertz. FM again takes up about 15,000 hertz. So that being said, you can understand now why, if we look at our frequency spectrum stuff and available frequency charts, why don't we use FM on very low frequencies where the band is fairly small?
A lot of hertz.
A lot of hertz takes up a lot of space. We also have something called ATV, which is known as high scan analog. If you're familiar with old school television stations, this had a bandwidth of 6, not kilohertz, but 6 megahertz. So where would we typically use this? We actually are allowed to do this. It's called amateur television. And this uses the NTSC standard. So where would we use that? Well, if we need 6 megahertz to do it, we would probably want to put it someplace where we have a lot of available bandwidth, right?
UHF?
Yeah, we do. This is typically UHF because there's a lot more bandwidth available. And we take a look at our frequency spectrum, our frequency allocation chart. We see that, in fact, notice on 70 centimeters, right here, this blue area, that's amateur fast scan television. On 900 megahertz, we have multiple channels. On 23 centimeters, we have 1240 to 1246, and so on and so forth. So it is very important to understand why modulation is what it is and why we do certain things in certain places. So let's look at repeaters, VHF and UHF. Because we have enough bandwidth available, we use either frequency modulation or phase modulation. Phase modulation is where we take a sine wave and we shift it left or right in time. It doesn't change the frequency, it changes the phase. And we can use that for voice as well. We can also, using that same handheld radio, for instance, we can do packet. Packet is digital communications over FM. Amplitude modulation, single sideband is a form of amplitude modulation. It's only half of the signal. And if you're curious as to why we do upper and lower, by convention, 10 megahertz and under uses lower sideband, and 10 megahertz and up uses upper sideband. And I think it really just came down to a long time ago what sideband was easier to generate on a given frequency. For long distance weak signal contacts, we use single sideband. So we could use FM, except that FM has a really nasty habit. The nasty habit is that if we are listening for a signal to be, let's say, right here, and it shifts like this, and it contains all these different frequencies in it, What we typically do is we take something called a limiter and we take everything above a certain level in our receiver and we knock it down so that everything is flat. So this is our block that we're looking for right in here. You know, let's change the color. This is the block of information that we're looking for. So now let's say that instead of one signal, we end up with two competing signals. One looks like this, a bunch of frequencies, and the other one looks like this. Those both end up in the receiver. Who wins? Who do you think?
They
Oh,
look
come
the
on.
same to me.
And the answer is that everyone loses. If there's one signal that's louder, like a lot louder than the other one, that one will win. If they're the exact same, both will lose. So FM is very, very is immune to noise. FM is very, very high. It can be very high fidelity, but at the same time, it has this thing called the capture effect, which says that only the larger station wins. Why don't we use FM on for aircraft?
Too much opportunity for interference.
Yeah, well, right. And what happens is if you've ever listened to air traffic control, if you have two stations transmitting at the same time, you'll actually hear both, which is good because if there's an aircraft that is in need of help, it might not have that strong of a signal, but you need to hear that it's calling Mayday. What if you have two stations on FM doing the same thing and one of them's nearby and the other aircraft that's calling Mayday is the weaker station?
You don't hear it.
That's
You don't
bad.
hear it at all. Exactly. So aircraft communications uses AM for that reason.
So Scott, question
Yeah.
for you.
Uh-huh.
Total noob question. I see SSB written all over the place for single sideband.
Mhm.
What is single sideband?
Single sideband is just this. You have an AM signal that looks like this. AM is a symmetric lower and upper sideband with a carrier. But because
So basically just a single band?
yep, and when you're generating the signal, you will choose the one that you want and you will filter out the other one and you'll suppress the carrier.
Ah,
That's single sideband right there.
got
That
it.
is upper sideband. If you were to switch to lower sideband, you would have over here.
So when we're saying SSB, we're picking which one we want?
Yep.
Is that okay? And is this applicable to all frequencies like,
Yep.
you know, VHF, UHF?
Yep, because it's
HF.
modulation. It has nothing to do with the frequency in use. It's only
Got
it is the modulation.
That helps. Thank you.
Okay. Okay. Let's see. Next one. For 10 meters HF, the 10 meter HF, VHF, and UHF. By the way, what are the limits on HF in megahertz, everybody? I told you I'd keep quizzing you. HF
30,
is
30 to
300.
300.
300,
HF 3 to 30.
Right.
VHF,
Uh,
30
30 to
300,
right? And UHF?
300 to 3000.
Okay. So for 10 meters, which is about 28 megahertz, and VHF and UHF, we use upper sideband by convention because it's above 10 megahertz. That's the break point. Single sideband has a narrower bandwidth than FM. Typical bandwidth of single sideband is about 3 kilohertz. Repeater FM voice signal is between 10 and 15 kilohertz. And the capture effect, only one signal on FM can be received at a time. An AM signal is AM fast scan TV signal is 6 kilohertz wide, or 6 megahertz wide. That's also known as an analog fast scan color TV. So if you want to put up your own amateur television station, you happen to have an old NTSC camera from a TV station, you can actually do that. Okay, Morse code. Morse code is another name for CW and vice versa. It has a very, very, very narrow bandwidth of 150 hertz, sometimes even less. An electronic keyer sends dits and das from Morse code. by using a left hand and a right hand paddle. One side says da-da-da-da-da-da, the other side says da 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 da. You combine the two and you get Morse code. Okay, digital communications, ones and zeros. That is the definition of digital. Packet radio is digital over FM. This is an FM handheld radio. If I tune this to the right frequency, we will actually get a squawk from our packet cluster. It takes me a minute to do this. 144390. Hopefully we hear it eventually. Let's see, what is included in packet radio transmissions? You get a checksum because it's digital. A checksum is the total number of ones in a byte. If it doesn't match the checksum, that means information got lost. And I haven't heard any packets yet. There was one. Did anybody hear that?
Oh,
Probably not. Yeah, okay. Well, I'll deal with it later. A header that contains the call sign of the station to where information is going, and an automatic repeat request. This is basically in case you have an error or a collision of information. ARQ is automatic repeat request. It essentially says, hey, that last packet was no good. I need it again. A packet is just basically a bunch of information. And packet radio is actually AX.25. It is the basic it is the basic backbone upon which the internet was built in the early 1980s. APRS, this is the automated packet reporting system. And APRS basically is a combination of all the information that we send over packet radio, which is, for instance, I could say my call sign, I could say what direction I'm going, what my altitude is, what the weather is, etc., and puts it on a map. So I will in a moment pull up aprs.fi, and we will take a look at a packet map. Okay, next. PSK is phase shift keying. This is a method of essentially taking a signal, and I guess it's really time for me to draw it. Oh, come on, whiteboard. Okay, so this is a sine wave. Everyone agree?
Yep. Yep.
Okay, I'm going to phase shift this sine wave. I have now phase shifted the sine wave. How many degrees are there in a circle?
360.
360 degrees. If I were to phase shift this whole thing by 360 degrees, that would mean that I have shifted it the entire length of the sine wave. If I shift it half of a cycle so that it looks like this, that would be a 180-degree phase shift. And this would be actually delaying it in time. So that would be a negative phase shift. I could also shift it back the other way so that the phase shift would be here. Oops. That would be shifted back that way. If I were to consider it existing in perpetuity, well, that would also be a positive 180 phase shift. Either way I get there, it's the same thing. So by intentionally modifying the phase of a signal, I can say, okay, if you're listening to a signal and you suddenly get a jump of the phase, you think it's supposed to be here, but all of a sudden it is up here. That would mean that in time, my signal looked like this. You'd have this discontinuity. That discontinuity, when you're listening to it, indicates that something happened. That could be either a value of a 1, or if it was a 0, it would go to a 1, or if it was a 1, it would go to a 0, depending on the code that was written. This instantaneous change is known as phase shift keying. By changing the phase, you have indicated that something happened that you want the other end to see. Okay, phase shift keying typically is a very narrow bandwidth signal. So for instance, 31 baud. 31 baud is about the speed that we can type. 31 baud generates a signal that has a bandwidth of about 31 hertz. That's really, really, really tiny. We actually heard one of those signals out there today. DMR is digital mobile radio, is an FM digital communications method. It essentially codes voice digitally so that over a period of time, each of two signals gets 1/2 of the time. So like here's a repeater channel. This is our repeater. This is, let's say, 15 kilohertz wide. Looking at it over time, as we go like in time, we have two different groups of people who are using the exact same signal. This is group A, and this is group B. And because they're separated in time and everybody is synchronized, here that's his name. Because everyone is synchronized who's on a particular group, the people in group A don't know about the people in group B, and the people in group B don't know about the people in group A. This is multiplexing, and it's time division multiplexing, and this is how digital mobile radio works. It basically allows two groups of people to use the same frequency half the time each. Which of the following is supported by WSJTX? So that's Earth, Moon, Earth. We covered this a little bit yesterday afterwards. Earth, Moon, Earth is also known as moon bounce, weak signal propagation, and meteor scatter, aiming signals up at meteor trails. WSJT, one of the most popular ones that people use, is FT8. FT8 is a very, very slow, very weak signal mode. The reason it's so slow is because the modulation is very slow. It takes up very little bandwidth, and there's a lot of redundancy. The nice thing about all that redundancy is that if you lose 50% of your information, you can still figure out what it was. So it's very, very good for lousy conditions or for weak signals. A mesh network. A mesh network is essentially a system that uses Wi-Fi equipment, so 2.4 gigahertz, 5.8 gigahertz. And because those are right next to ham bands, you can go through, modify the equipment, change the power levels, change the antennas, and it creates a self-healing data network adjacent to the original Wi-Fi frequencies, but with modified firmware that makes it ham radios. Okay, did somebody ask a question there? Nope. Okay. All right, so we're into station setup and operating controls. We are skipping past what we did yesterday. We are now on page 73. Okay, so whose law tells us that it's a good idea to do something like this? We have our battery, and we have our equipment. We'll call this a generic load. Whose law tells us that it is a good idea to make these wires connecting the battery to the load short and fat? Whose law? And
Ohm?
why? And Ohm's law, and why?
Less resistance.
Less resistance, because a wire is, the wire's resistance is based on the cross-sectional area and on its length. So if you have a thin, long wire, it will have a very high resistance. Well, your load, let's say this is a 12-volt battery, and your load draws a current of 10 amps. Well, if your load wants 10 amps and you have a resistance in ohms, what does Ohm's law say? E is equal to what?
I times R.
I times R. Okay, so if E is equal to 10 times, let's say we have a 1 ohm resistance, what is the voltage drop right there? That is 10 volts. We only had 12 volts to begin with, and we lost 10 volts in there. So how much voltage is left for our radio?
2 votes.
2 volts. Who knows of a radio that'll work well on 2 volts? I don't.
I don't know.
Yeah, exactly. This is a problem. So the fix is that we can take that resistance and instead make it 0.1 volts or 0.1 ohms, in which case our voltage drop is now 1 volt. And now we have 11 volts left to run the radio. We're getting closer. One thing we can do is we can say, okay, well, our battery is actually 14 volts. Our battery is 14 volts, and we have 1 volt drop. Now we're down to 13 volts, and everything will still work. Ohm's law
So-
says make your cables as short as you can and make them as thick as you can to reduce voltage drop. Okay, appropriate power supply for a typical 50-watt transmitter. A 50-watt transmitter. Okay, so let's do Ohm's law. Somebody give me Ohm's law for power. P is equal to what?
I times
I times E.
R.
Our
E.
our battery is 12.5 volts. Our power for our transmitter is 50 watts. How much would our current be? What's our current?
Wouldn't it be P over I divided by R?
4? It would be
It'd
4?
be 4 amps. Yep. Right, because we don't know that. So it's 50 divided by 12.5, which is 4 amps. Okay, so we have our 4 amp draw. So why is it that we need to have a power supply that is about 12 amps? Why do we need a 12 amp power supply? You look at those numbers, this is capable of supplying 150 watts. To run a 50-watt radio? Why do you think? Come on, somebody give me some ideas. Does it have any lights? Does it have a display you can read? Does it generate? Does it have an LED display, LCD display that has backlights? That uses power. Does it have a speaker? That uses power.
Yeah, so accessories, right?
So accessories, and also the fact that if I'm using an amplifier, what does an amplifier do? It uses it pushes current down this way and uses more current this way. What happens to some of the current? Well, it goes through a resistor. What does the resistor do? And what does the transistor do? No transistor in the world is perfect. So what does that mean? What's its efficiency?
You have energy loss.
It's less than 100%. So in order to make this work, typically what we'll end up with is we assume a conversion efficiency from DC power to RF power of about 50%. So in other words, to make 50 watts, we need 100 watts. And so why do we pick a bigger power supply? Because we're probably going to hook something else up at some point. So that's a good nominal starting size. It's 12 amps.
So in my mind, when I think of a power supply, I think of volts. That is, a power supply is providing volts, not amps.
Well, yeah, but it provides amps are more important or as important.
So you look for a power supply that provides X volts and amperage that it can produce.
So let's take a look
Amps
at,
is current draw, right?
it's yes, but it's available current.
Okay, it's available current too. Okay, so you need to look at both
So let's
in the
just
power
quickly
supply.
take a look at this. Here are power supply. Notice PowerWorks, it's 12 volt power supply. What's its capacity? 30 amps.
Yeah, 30 amps.
Right.
Okay.
Here's another one. All right, so here's in the specifications, 5 to 15 volts variable, output current maximum 32 amps, 30 amps continuous. So
Okay.
every power supply, that's actually, it's actually two things that are really important. There's its operating voltage and its available current.
Okay, good. That was a good mental picture. I can remember that.
Okay, good. Okay, next. Connecting a computer to a radio. Okay, so what does a computer have that you can listen to? You may be listening to it right now.
Speaker.
Speaker. Okay, so a computer has a speaker output. And what are you talking into?
Microphone.
Microphone. Okay, so how does a radio work? We're going to put a radio on the other side. What do you talk into on a radio?
Speaker.
You talk
Transmitter.
into a microphone. And how do you listen to a radio?
Speaker.
A speaker. Okay, so the way that this works is you take the microphone of the computer and connect it to the speaker input of the radio and the speaker output of the computer and connect it to the microphone. Now, the other thing you have is a button on the side of a radio, whatever that radio is, or on the microphone, which is known as a push to talk, PTT line. Somehow the computer has to have a circuit which triggers the radio to switch with the push to talk line from receive to transmit. So those are the three things you need when you're hooking up a radio to a computer. That's a simple radio to computer interface. You have to transmit the audio back and forth, and you need to be able to have a push to talk line that keys the radio and changes it from receive to transmit. Now, very often this over here is a sound card. In a lot of today's radios, you will not actually even have that. What you will have is that the radio, in fact, ends right, whoops. The radio actually ends right here at the sound card. The sound card is built into the radio. And if that's the case, you have a USB cable that just connects the radio to the computer. And that's in fact what most radios, what most equipment today is provided with. Sound cards are so ubiquitous and cheap that it's just easier for manufacturers to build a sound card into the equipment. Okay, let's see. How are the transceiver audio input and output connected using FT8? FT8 is digital. So in order to do that, audio input and output of a computer running WSJTX. You just have to basically pipe the audio from the radio to the computer and vice versa. Computer line in, that's your microphone, goes to the transceiver speaker connector. Computer line out goes to the microphone input on the radio. But you can always just redraw the drawing when you get the scratch paper. Okay, if you get distorted audio, there's a couple things that can cause distortion on your audio. So here's a question. What again is this? A piece of wire. What is this piece of wire? Another piece of wire. Any piece of wire can function as what?
Capacitor.
It can, but what does any piece of wire also function as? Piece of wire by itself. That's right. If it's carrying current, it generates a magnetic field. Another piece of wire that is in the magnetic field will do what?
Inductor.
It's a conductor, and so what happens? It induces a current in the wire. Well, if this is microphone audio, what gets picked up by the second wire?
Some of the audio.
Some of the audio. Yeah, this is called crosstalk. We don't want this. So the way that we do this, the way that we prevent this from happening is we take this signal right here and we build an enclosed environment for this wire. And then we ground this wire so that if there's any magnetic field energy that's existing around it, it gets shunted off to, if there's any current or anything like that, it gets shunted off to ground. The same thing with the other one. If there's a magnetic field that's being formed, We take this and we ground this wire.
So that's similar to a Faraday cage?
Essentially, yes, it's a small Faraday cage. It takes any current that would be around, and instead of getting onto the wire of interest, it shunts it down to ground. Now, the other thing we can do with this is, let's say that you have a signal that is traveling along this wire. And we have decided that we're going to use a microphone cable like this, and you actually do have a current flowing this way. So what does the current on the outside make? A magnetic field.
Right.
Okay. So that magnetic field, we want to be able to do something with it so that it doesn't get out into the world. One thing we can do is we can actually use something called a ferrite, which looks like this, like a donut, which is a paramagnetic or diamagnetic material, or ferromagnetic, depending on how it is. And what this does is that this is a just like a transformer, and in fact, the same materials can be used for that. This is a preferred path for magnetic field lines to exist. Well, when the magnetic field lines wrap around inside that material, the energy has to go somewhere, and they actually tend to warm this up. Well, once they've warmed it up, it's been dissipated as heat, and then the magnetic field lines aren't as strong. So if you have another line over here somewhere, the chance of it being coupled together is quite low. If anything does make it over there, you put another ferrite on this that looks like this. And if there's any magnetic field that's being generated, it gets to the ferrite and it finds a preferred path to be taking. It just dissipates it as heat. Has anyone ever seen a ferrite on anything that they have? I'll bet the answer.
No, I didn't see. Can we see one of those?
I'll bet the answer is yes. And you've got one probably right near you right now as I unshare this. Anyone have a power supply that has something like this?
Oh, yeah.
That is a ferrite choke. That's a ferrite bead. It's essentially a donut of a mix of powdered iron and cobalt and blue that's been baked into a shape so that if there's any AC noise on this signal, on this wire that has, that could get into your computer, it will basically be dissipated as heat by that thing.
Is that what's used to stop ham interference with neighbors?
There's filters, there's ferrite chokes, there's lots of different tools. And in fact, my biggest problem was that my transmitter would wipe out my computer. So that every time I keyed down my transmitter, I would the USB cable would cause the computer to lock up and I'd have to reboot it. So I fixed the problem. You know what I did? So here's my USB cable. And I took a ferrite and a ferrite and a ferrite and a ferrite and a ferrite. I have 5 ferrites on my USB cable because I found that it was particularly sensitive. So why did I use 5 ferrites? Come on, somebody has to know this. What do you think?
Hey,
correct.
To dissipate any electrical energy.
Yeah. Well, the reason I used 5 is because I tried 4 and 4 wasn't enough. My computer's still locked up. So I experimentally kept adding stuff until it went away. I found that 5 ferrites worked where 4 didn't. So that's the solution. A lot of this is experimentation. Okay.
So you took a USB cable,
yep.
You cut it,
no,
put a ferrite in it?
There was a split. They're split ferrites. They're 2 halves and they clip together.
Oh, so you just slide it over.
And clip it on.
So where can you find those at then to buy if you want to buy them?
Well, it's funny that you would ask that because there are many companies out there.
Your friendly neighborhood ferrite store.
Well, actually, that's actually true. Except that you used to be able to maybe go down to Radio Shack and get them. But now you can't do that. But what you do have is, if anyone
That
has
or Heathkit.
this company called Fairlight, notice they have engineering kits and cool stuff like that. You can also go to products and suppression components. So let's see, EMI, suppression, ferrite beads. You figure out what frequency you're trying to suppress. Notice this different material. That's a different combination of metals mixed with glue that's baked into a shape. You pick your dimensions. You pick the frequency that you want it to work at. Notice that they're rated differently at different frequencies. Notice you have different materials. There's material 61, 43, 73, and like for instance, 73, it works very well at 1 megahertz and 25 megahertz. A different material, let's go up to like material 61, works at 100 megahertz up to 500 megahertz. So different materials, these are basically just different metals that have been crumbled up into a powder, mixed with glue and baked into a shape, behave differently, magnetically speaking. Pretty cool stuff, right? So the question is now, where do you find these? You can go to any electrical supply shop that exists. So you can go online, you can go to Mouser, you can go to Allied, you can go to they're in Thief River Falls, DigiKey, any of the big supply houses. You can buy any ferrite that you want. I have kits of them of different sizes and shapes and frequency responses, just because I never really know what's going to work. I can guess, but and sometimes you'll actually find like somebody getting you go to a swap meet and somebody has like a bucket of miscellaneous ferrites of different sizes and shapes that they've collected over the years, and just try it out. If they're selling them for $0.25 a piece. Which of the following is preferred for bonding at RF? That would be flat copper strap. Okay, does everybody remember yesterday when we talked about that thing called the skin effect? As frequency goes up, where does current like to flow?
Towards the outside.
Toward the outside. Okay, if you have a certain amount of copper, how do you maximize its surface area?
Flat.
You squash it flat. So a flat copper strap provides less resistance to radio frequency energy current flow than a round conductor. Okay, now, remember we said yesterday about charging a battery? Where should the negative power return of a mobile transceiver be connected in the car? Now, the entire frame of a car is ground. That is defined as your ground, right? And let's say that you have a light. And so here's your battery, and it's a plus and a minus. And it goes like this, and you have your plus, and it goes through a fuse box. And somewhere back here, you have a light. Let's call it a tail light, right? The negative side of the tail light just gets attached to the frame of the car. The frame of the car goes like this. Here's the car frame. And this goes to here as well. What does this require this to do? That's the frame of the car. The frame of the car becomes part of the circuit, right? In order for this to work. What if you add a transceiver right here that has a plus and a minus terminal? And you go like this, you connect to this, and this transceiver, this light, let's say uses a current of 1 amp. That means you have 1 amp of current flowing through the body of the car from that light bulb. Now, let's say you put in a transceiver that pulls 22 amps of current. Where would you want to connect this back to? Well, one part of you says I could just go right here to the frame of the car, right? But then how much current do you have passing through the frame of the car?
A lot.
A lot. It is not necessarily designed for that. Besides the fact that what did we know? What did we figure out about Ohm's law? About this wire versus this wire? Which one has lower resistance?
The thicker one.
The thicker one. And since you don't know how the car body was built, you don't know what the resistance is. I mean, it's ground-ish as far as this goes, but it's not necessarily an ideal ground. So what you're going to do is instead of connecting it to the body of the car, you're actually going to take this wire and run this straight back to the battery.
You mean negative, negative?
No.
Oh,
Right.
Right to the
The positive of the battery
uh-huh.
to the positive terminal of the radio, and then the negative to the negative.
Oh,
So it's basically a circuit.
Otherwise, it's a short.
Right. This is because this is a load.
mm.
So does that, you're saying then that the battery, negative side of the battery is a better ground conductor than the frame of the car?
Well, not the negative side of the battery, but the conductor that you provide. These wires that you provide, you know what they are. You know what you put in there. You
So
know
in
what
this
they are.
example, you just have two batteries in the series.
Well, no, that's only one battery. Notice it says load. This is the radio.
Oh, I'm sorry. Okay, yeah.
You're going to run it directly off the battery. And in fact, some people actually have a separate second battery just for running this stuff. So that it doesn't drain the car battery.
Mm.
In fact, so people who have, does anyone here have an RV? There's always somebody. Does anyone have an RV?
I
I've
do.
had one.
You have a separate you have a separate second battery for your other stuff?
I have 8
No.
batteries because
There you go.
it's set up for off-grid travel.
There you go.
And I as well.
Yep.
1400 amp hours of lithium.
Yep. So it has
Yeah, my pickup has a separate charging system for an external battery.
Yep. There you go. It's the same thing. Okay, so now we get into batteries, and we're about to get into operating controls. We're going to take a break right after this. How can you determine the amount of time that a battery will work? A battery, any battery, has something called a capacity. The capacity of the battery is either measured in ampere hours or in watt hours. Ampere hours is a much more useful thing as far as I am concerned. Essentially, this means that this is the number of amperes that it can deliver for the number of hours, and you just multiply them together. So if I have a battery that is 100 amp hours, didn't you say you had 1400 amp hours of lithium ion? Did I hear that? So,
Somebody did.
yeah. So 100 amp hours means that I could supply 5 amps for 20 hours, or I could supply 10 amps for 10 hours, or I could supply 1 amp for 100 hours. Essentially, this is a measure of the amount of electrical oomph, electrical stuff available from inside the battery. A bigger battery will have a bigger capacity. A physically bigger battery will have a bigger capacity than a smaller one. So again, this is known as its capacity, and it's measured in ampere hours. Sometimes you'll see something measured in watt hours. Well, what's a watt is equal to a volt times an amp. So to get watt hours, you would just basically take the ampere hour rating and multiply this by voltage. But I don't find, usually when a battery is specified, it will be like 13.8 volts DC at 100 amp hours. That's typically the rating that you'll see. And then if you're pulling 13.8 volts, you have 100 amp hours capacity, and you can figure out how long a battery is going to last for a given application, and also how long it'll take to charge. Okay, how about a 5-minute break, everyone?
Yep.
All right.
Perfect.
Okay, everybody.
Scott, I got a quick question for you.
Yeah.
On test day.
Yep.
Being I'm actually out camping right now,
Uh-huh.
can I test in those surroundings? I just turn on my screen.
If you have a signal, sure.
Oh, okay. So,
Sure.
no. Okay. So just my picnic table right here in front of my coach. Nobody's around.
Somebody will say, okay, let's see your surroundings. And they'll say, okay, everything looks sterile to me.
All right, perfect.
Yeah. Okay, we are into operating controls. And for this, I will bring up this, our handy dandy SDR, which is our software defined radio, which I found to be one of the best teaching tools. Okay, so notice we are now looking at a Morse code signal. Operating controls. We can affect certain things like squelch. And so here's squelch. Squelch mutes the receiver when there's nothing of interest to hear. If I were to tune down to here, it comes back. I could also turn the squelch off. And by the way, that's called chirp that you hear. I can also adjust the filter bandwidth. When we're talking about filter bandwidths, see what we just did? We just adjusted the filter bandwidth. There's actually a picture of a filter. Isn't that cool? Here's another filter over here, moved over to another signal. Now, this is why it's necessary sometimes to pick a different filter bandwidth. Let's go to 14.34320. And let's go find a single sideband signal. So now we have a very narrow filter connected. How much of the signal do we hear, everyone? Because what is the approximate bandwidth of a single sideband signal? We just covered this. Anyone remember?
6?
3 kilohertz.
Great.
So we're going to set this out to 3 kilohertz. There we go. Now we could, if the conditions were a little noisy, trim this down a little bit. That's 2400 hertz. Notice also, as we have this, I want you to notice that we are on upper sideband. And how do I know that we are on upper sideband? This says right here, upper sideband. How do I also, looking at this picture, know that we're on upper sideband? Does everybody see that little vertical line at 14.318, right where my cursor is? That is the carrier frequency. Notice what we have. The signal is above the carrier frequency. That's how I know we're on upper sideband. Another thing I can do here is, let's say that we're going to switch to the other sideband. I'm going to pick lower sideband. Notice that my carrier frequency is now at the right-hand side, and the signal, it says, is now below that. Notice what we now have. Can anybody understand that? I hope not. That speech is completely inverted. The highs are where the lows should be, and the lows are where the highs should be. So now this brings up another very interesting and important point. Let us say that we switch back to upper sideband, and our frequency band goes up to 14.350. And in fact, look, there's somebody up there. Around 14.346 is the dial frequency on the left. So notice this little indicator here says 20 meters upper. That is the upper limit of 20 meters. Let's say that we were listening to a signal and it was right where my slider is, and some of the signal extended past 14.350. Would that be a legal signal or not? What do you think?
It's a bleed.
It bleed. So the rules are, we're going to be getting into this very shortly. The rules say that your entire, because we're not channelized, it just says that our frequency band is 14,300 to 14,350 on the 20-meter band. That means that every part of every signal that is transmitted inside the band has to be completely inside the band. Every so often, you'll see a signal, instead of being like right here, will be right here. We know that the signal is 3 kilohertz wide. We tune to 14,348 to hear it, and lo and behold, there is part of the signal sticking up above the high edge. We have to be able to, we have to understand these things to make sure that we operate legally. Our entire signal has to be inside the band.
How did you know your signal was outside because of the width of that
Well, you
slider?
tell me, how wide is a single sideband signal?
3 kilohertz.
3 kilohertz. If my dial frequency, which is my carrier frequency, is at 14,348, and you add 3 to it, what are you going to get?
Yeah, you're going to cross over 350.
You're going to cross
so
over.
you don't choose.
You don't tune above
frequencies
14,347 if you're on single sideband, upper sideband.
Right. Okay. Because that was a test question of that.
Yep.
And I think I missed it, but
now you
we
won't
hadn't
miss
covered it yet, so I
No.
forgave myself.
Yes, now you won't miss it.
Yeah.
Okay. The use of excessive microphone gain on single sideband or any transmissions is the effect of me doing this and sticking the microphone in my mouth. Distorted audio. What's the result of tuning an FM receiver above or below a frequency? That means that those frequency excursions in the signal are not in the right places, and you're going to sound distorted. Which of the following can be used to enter a transceiver's operating frequency? We just did that by moving the slider around. That's basically a VFO. A VFO is a variable frequency oscillator. That is a physical knob that you turn. We actually could also use a keypad or a slider. Those are all ways of altering the frequency. Don't get fooled by the CTCS or DTMF. That doesn't make any sense for this question. To enable quick access to a favorite frequency, you store it in memory. The scanning function of an FM transceiver allows us to scan through a bunch of frequencies quickly. We just did squelch. Squelch basically mutes the audio when there's no signal present. How do you listen to a weak FM signal? You set your squelch completely off. You basically open up the squelch so that the signal is always heard, even if it's all noise. Okay, repeater offset. So this is a repeater. Repeater is on a building or a mountaintop or something, and a repeater will have a transmit frequency that is published. Let's say 146.720 megahertz. That is the transmit frequency of the repeater. The repeater is a repeating station. It's literally like somebody sitting on top listening and simultaneously yelling out to everybody else. This repeater will also have a receiving station that is offset by a certain amount. On the 2-meter band, the offset is 600 kilohertz. And this is in megahertz. And it's plus or minus depending on where it is. In this particular case, it's a negative offset that will be published. So that would be on 146.120 megahertz that it will be receiving, which means that if somebody wants to access the repeater and give it a signal that has a chance of being retransmitted, this person down here will transmit on 146.12. This other person, in listening for that station, will be listening to the repeater, listening to what's coming out on 146.72. Now, if the person who is on the right-hand side wants to transmit into the repeater, they want to answer, they will be transmitting on 146.12. And this other station who was transmitting now wants to listen, they'll be listening on 146.72. So basically, when you have a handheld radio or a mobile radio or whatever FM radio, you program in the offset frequencies so that when you switch from receive to transmit, you change frequencies to match what the repeater is listening for and transmitting on. That is known as an offset. That offset, again, on 2 meters, it's plus or minus 600 kilohertz. On 70 centimeters, it's plus or minus 5 megahertz. Those are your offset frequencies. Now, there's also something called a tone squelch. Tone squelch is either CTCSS or PL. This is a subaudible tone that goes from either 67 to about 250 hertz, which is lower than we are used to listening to in frequency. And this is superimposed on your transmitted signal. This is kind of like a little key that has to be transmitted with your signal and with this person's signal to allow the repeater transmitter to function. If that signal is not there, let's say that a repeater is published as having a PL tone of 100 hertz. If you do not have that 100 hertz signal transmitting at the same time, your signal will not be received and you will not be able to access that repeater. And that's either known as a PL or CTCSS. There's also something called a DCS, which is a digital carrier squelch system that is sort of in parallel with the PL tone. And this is a sequence of frequency stepping that a signal has to jump up and down at in a certain pattern, a very small distance frequency wise. And if it does, then the repeater will activate. Otherwise, the repeater will not. Okay. Let's see, moving along. Okay, digital mode hotspot. A digital mode hotspot is basically just like a receiver that is on the internet that basically provides you a gateway for connecting a digital voice system to the internet. So there's a lot of hybridization between radio and the internet now. A lot of communications, in fact, like digital mobile radio and Arden Mesh, they actually work on TCP/IP networks. And so it's actually quite easy to put up a bridge to kind of bridge the gap between a radio-based network and an internet-based network, so that the radio system can be used for local communications. And then there's a gateway that provides a link to the internet, and then a longer haul communications, even on VHF or UHF, which is usually line of sight, can be transmitted somewhere else. And you can have a handheld radio that can talk to somebody in Australia quite easily now. A talk group on a digital repeater is a way for groups to use a channel at different times. That's kind of like the talk group A and talk group B. You program your code, and then you are then part of that group. That gives us the ability to have twice as many people on a particular repeater at one time. A DMR, DMR is digital mobile radio. There's a code plug. A code plug is essentially the entire programming for a repeater and its talk groups. And some code plugs contain up to 200,000 different repeaters because they contain internet-based repeaters as well. So all you need is a local connection or a hotspot, and then that connects to somewhere else. And all of a sudden you're on a repeater, let's say out of the Netherlands, with 20 other people in your talk group from 12 different countries, just on a handheld radio. So long as the internet stays up, it works really well. How is a specific group of stations selected? By entering the group's ID code. Essentially, that says we're in group A, group B, group C, etc. That will allow the radio to select who it's going to listen to at any given time. There is something called a repeater color code on DMR systems. It has to match the radio. Your radio has to match the repeater it's using. It's just another way of identifying what you're using hardware-wise. D-Star is a competing technology to DMR. The D-Star system is a little bit, even a little bit more complex, because D-Star also transmits your call sign digitally when you key your radio.
You also have to register for D-Star.
And you have to register for D-Star, yes. The advantage of having multiple receive bandwidths, it permits noise or interference reduction by allowing you to select a particular mode specific bandwidth, like we just did with Morse code and we just did with voice. For single sideband, a narrow filter, 2400 hertz. Okay, this is another one, the RIT or clarifier. RIT stands for receiver incremental tuning. And what it allows you to do is change the receiver frequency without changing the transmitter frequency, essentially unlocking the two. One reason you may need to do this is because, well, let's say that I am talking with somebody who's using a radio from 1960. They actually have a separate receiver and transmitter tied next to each other. And they have two separate variable frequency oscillators, and one of them is slightly off from the other. Well, if I hear somebody and they don't sound like they're on the exact correct frequency, if I change my receive frequency, that also changes my transmit frequency. Well, if they hear that, then I'm now off frequency on their end, and they will tune again. So you will continue to basically be mistuned. Somebody has to be able to separate the receiver and transmitter. The RIT allows you to do that. PTT is push to talk. It switches a transceiver from receive to transmit when grounded. Okay, station equipment. So we are now on page 81. A transceiver, that is a portmanteau of the word transmitter and receiver, transceiver. Transceiver is a receiver and transmitter combined. A transverter is a transmitter converter. It allows you to transmit in one place on one frequency, and with your signal comes out on a different frequency. Now, how do you achieve something like this? We use something called a mixer. A mixer is a device that basically is drawn like this and has a frequency here, frequency 1, and a frequency 2 that are sent into the mixer. What a mixer does is it combines those two frequencies and generates outputs of frequency 1 and frequency 2, but then it also does sums and differences of the two. Frequency 1 plus frequency 2, frequency 1 minus frequency 2, frequency 2 minus frequency 1, 2 times frequency 1, 2 times frequency 2, and lots of other combinations. Which means, let's say I have 30 megahertz over here and 60 megahertz over here. Let's say 160 megahertz. Okay, so what are the outputs that I'm going to get on the right-hand side? Somebody walk me through this.
190 megahertz.
Yeah, I'm gonna get 30 and I'm gonna get 160 because those are the fundamentals. But then I'm gonna get 190, and what else?
Yeah.
130.
130. What else? Well, there's a negative signal, which is negative 130, which I don't know how that's going to work, but it still exists in theory. It's just phase reversed. I'll also get 2 times it. I'll get 60, and I'll get 320, and I'll get a whole bunch of other stuff. Well, the target that I want is this 190. If I were to put this on a graph, it would look like this. Here's the 190, here's the 30, here's the 160, and some other stuff out here. How do I get just the one that I want? What do I build? What do I make?
Sideband.
Looks like this. What is that called?
Filter.
That's a filter. Yes. I build a filter. And what are filters made of?
Capacitor and coil.
Capacitors and inductors. That's it. I build myself a bandpass filter so I allow the wanted frequencies to go through and block all the other ones. This is known as a mixer. And this is the heart of something called a transverter. And interestingly, if I reverse this and instead I have, instead of 30 megahertz going in, I have 190 megahertz going in. Remember, my original frequency going in was 30. What am I now going to have coming out? One of them is going to be the subtraction of the two, right? And that will give me 30 megahertz back. So on receive and transmit, this system is designed to switch around and work backwards. So this would be a transmitter or a transverter that goes from 30 to 190 megahertz. I just sort of picked that out of the blue. Not a ham band, but you get the basic idea. Depending on which signal goes in which way, that determines what comes out. And I can filter for that signal too. Filters are incredibly important in this case because let's say that this is in a ham band and this is in a ham band and all this other stuff is not. The requirements say that all of those other signals have to be, depending on the band I'm on, either 50 or 60 decibels below the peak that I'm aiming for. So if we have 60 decibels lower, what does that mean? What does 60 decibels translate to?
Well, that would mean you're on, right?
What? Let's break up 60 decibels. How do you do 60 decibels? You do 10 and 10 and 10 and 10 and 10 and 10. And every time we have 10 decibels, what does that mean? A factor of what?
3.
No.
10.
Nope.
That's
10.
right. 10.
10.
So
That's
it's
right.
10 times 10 6 times is 1,000,000. And because we're at negative 60 decibels, it's 1 over 1,000,000 or 0.000001. So if I have a 1 watt transmitter, that means that all the other signals have to be that big or smaller. How important are filters now? What do
So
you think?
important.
So important. Filters are what makes all of this possible. Filtering is incredibly important.
So we've talked a lot about filters and you're talking about different bands and widths and everything
Mhm.
and making a filter or using a filter. So in radio equipment, does filtering come built into it and you just adjust to it? Or, I mean, the way I've been
Some of
thinking
it's
up till now,
adjustable. Some filters
is-
can be adjustable and some of them are fixed.
yeah,
Some
but
of them you will pick a different filter pack by changing bands. Or when you switch from band to band, it brings a different filter unit into play.
right. So your equipment is capable of doing that for you. You don't have to go build physically all these filters. Now, sometimes you do.
Well,
but
here's the question. Are we allowed to build our own gear?
yes.
Then you have to build your own filter and you have to know how to do it.
Well, yeah,
That's-
if you're going to
so,
build,
yeah, that's right.
but for the simple minded guy that's not going to be out there with electronics and building,
Yep.
equipment you buy comes with the
typically have.
functionality and capability.
Correct. And
Okay.
it has to, or else it can't meet type acceptance. Because in order to be usable, it has to meet certain limits. For instance, let's say you
Requirements.
go and get a
Okay.
system. Let's say you go and you get a handheld that is designed to operate from 420 to 450. Okay.
Mhm.
So the second harmonic of 450 would be 450 times 2, which would be what?
900.
900. That is right below this. So what would the third harmonic be? This times 3.
12, 1350.
1350. That is not in a ham band, is it? Our band up here ends at 1300.
Yeah.
Who's in that band? I don't know.
Hmm.
Well, what it means is that if let's say that is air traffic control,
Hmm.
and the third harmonic is a real thing, So let's say you build, because we are allowed to do so, an amplifier for 450 megahertz, and it puts out a spurious emission, or it puts out a third harmonic at 1350, which is right in the middle of an air traffic control band or something, or air traffic radar. We are allowed to do that. However, we are not allowed to do something we are not allowed to do. So if the requirement is that any piece of gear that is on the air has to have harmonics that are 60 decibels down from the fundamental, that means that you actually have to test it. And let's say that you end up interfering with air traffic control because you're generating a harmonic of that 450 that is at 1350 and it's only 40 dB down. The FCC will come find you. The FCC will come find it.
Yeah.
Because you're interfering with somebody. So the reason those rules exist, the reason that one of the reasons that we have to take a class is because we have to understand decibels, because decibels are the key to understanding interference. And we are not allowed to interfere with other services.
Okay, that clarifies.
If we weren't a group of people that were able to build our own stuff, none of this would be important. But the thing is that your license gives you the privilege of being able to build your own stuff. Even if you never do it, you have the privilege of being able to, which means you need to know what it means.
I think the question was,
yep,
can we just purchase a system that has what we need already in it?
Yeah, if you buy an off-the-shelf radio that has been type accepted, it's got an FCC stamp on it, it will meet the ratings. It will have the necessary filtering to do the job.
Yeah, and I think, probably besides myself, there's probably a lot of people that came into this class thinking, well, I'm just going to go, and buy a radio that has this, and that, and I'm going to use it and everything's going to be fine. I just need to know how to operate. We can do that. That's the simple end over here.
Yes.
But because we're licensed, we're now able to start playing with stuff.
You have carte blanche. You have carte blanche to build something. You are allowed to build your own receiver. Yep.
So how does a transverter look like then? Is there a picture of a transverter?
I will show you a transverter in a sec. Okay, device that increases the transmitted output from a transceiver is an RF power amplifier. Now, given what we now know about VHF and single sideband, okay, single sideband is what kind of mode? An amplitude modulated mode or a frequency modulated mode? Amplitude. Okay. Well, if the amplitude is important and this is your signal and you're making a bigger copy of it, does it matter if it's an exact copy to you? Yes or no? I hope so. Otherwise, it'll be all distorted. So what that means is that if we're using a transistor to make a copy of this, if we are doing this, this is the transistor output curve. We are going to be operating in this range where the transistor puts out a linear, there's a linear relationship that when you get bigger input signal, there's a proportional bigger output signal. Again, this is called the linear region. If we're doing FM, FM is a frequency modulated signal. All we need to know is that it contains certain frequencies. Do we care how big they are? If they're that big or if they are this big. What we do when we get to the receiver is that there's a limiter and it caps, it basically chops off anything above a certain height. So it doesn't really matter if it's the same all across the board. So if we're using FM, we can actually use this part of the output. And what happens is that if we do this low part down here and this part up here, that's actually more efficient than using the linear part. So when we go to use an amplifier, when we buy one, for instance, or build one, there will often be a switch that says FM CW, FM, CW, SSB. Single sideband requires linearity. It actually biases the amplifier in a different place so that it functions differently. Single sideband is different from FM and CW. FM and CW don't require that in order to work properly. So that's why you have a switch on an amplifier that you buy. Okay, let's see. What determines the ability of a receiver to detect the presence of a signal? That's the sensitivity. If you have, for instance, a hearing aid will increase the sensitivity of your ears by being able to listen to quieter things and then amplifying them. Selectivity. My wife says I have selective hearing. I choose to not hear things that require me to clean up the house, for instance. That would be selectivity. I have the ability to essentially filter out things that I don't want to hear. That's known as selectivity. An RF preamplifier, we did this yesterday when we talked about Earth, Moon, Earth systems. You can't amplify what you can't hear. So if you're listening for something that's really, really faint, you're going to put a preamplifier all the way up by the antenna. A device that converts a signal from one frequency to another is called a mixer. And again, the mixer is at the heart of what other thing? Remember what that's called?
Transverter?
Yep. Okay. And right now I'm going to show you a picture of a transverter. It's a very boring looking device. When you go buy a transverter, it's got an input and it's got an output. That's it.
Oh, that's it.
That's a transverter. No knobs, no anything.
Wow.
Oh, it doesn't matter what frequency, what anything you're using, if you
Nope.
have a transverter in there
Just
like that.
It
It
linearly translates something to something else.
Yep. Automatic.
Yep.
If I could use
And
that
in,
word.
and in fact, this is what a transverter schematic looks like. Let's put one up. Let's see, overtone oscillator. And somewhere in here, there's going to be a mixer. Transmit mixer amplifier. Okay, let's find the mixer. I believe the mixer is right here, this U1. So it's basically just an operational amplifier or a double balanced mixer, or essentially it's a nonlinear device that is designed to be something that is kind of like, it puts out a dirty signal. We use that dirty signal, which puts out all other kinds of stuff, to our benefit in this case. And again, the schematic signal for a mixer is this. That's a mixer.
Speaking of schematics and symbols on the test, it asked me when's a capacitor in the schematic.
Mhm.
And all we've done was two parallel lines.
Yeah, you
And
can
the
also
right
draw it
answer had
otherwise.
a curve on it. One
That's a
line.
capacitor too.
Yeah, I flunked it, but now I know.
Now you know. Well, there's another capacitor too, which looks like this,
Yeah,
right? And that's a special capacitor. Know what that's called? Anyone? Okay, let's go back to how a capacitor is built. Okay, that's a capacitor, right? What do we put on the
Right.
inside? What do we put in between?
Insulation.
Insulation. Okay.
Insulator.
Yep. Okay. Now, if we want a higher value of a capacitor, we can physically make it bigger. Right. We can also alter it by changing the size of the gap in between. We can change its voltage rating. We can change its voltage rating by putting a different material in between. The other thing we can do is we can put an electrolytic, like a goo, in between the two. Now, what happens is that this allows you to get very high values of capacitance in a very small space. but it also requires you to make sure that you follow the polarity. If you follow the polarity, everything's fine. If you don't follow the polarity, what you end up with is a capacitor that looks like this with two leads at the bottom. And at the top, it has these 3 little or 4 little score marks. And you end up with all the goo squirting out from the top with a rather loud explosion sound. That's what happens if you hook up an electrolytic capacitor backwards. This will be marked with a plus sign on the positive terminal and a minus sign on the negative terminal, or just one of them or both. If you don't follow that and you hook it up backwards, essentially it will blow up and it will no longer work. So that's why you have an electrolytic capacitor, because you can typically get a very high capacitance value in a very small space. A circuit that generates a signal at a specific frequency is known as an oscillator. Normally, we don't like oscillation because it creates something called feedback. But sometimes if we can pick the frequency of feedback by using a certain capacitor and inductor combination, we can generate a frequency that we want. That's known as an oscillator. So if we were to build a mixer and we have one band that we want to put onto another band, for instance, we would have our mixer right here. And let's say we have 30 megahertz over here and we want 222. What would we do? What would be the frequency right there? 192 megahertz. So we would actually build an oscillator that would intentionally make a signal at 192 megahertz. We would pick our inductors and capacitors. Maybe we would also want to be able to tune it. So we would have a capacitor that we could have a variable capacitor and be able to change the frequency. Because the resonant frequency is 1 over 2 pi square root of LC. So if we have a variable capacitor, we can change the capacitance value, which changes the resonant frequency. So we can tune our oscillator. And that's known as a variable frequency oscillator for obvious reasons. Okay, symptoms, causes, and cures of common transmitter and receiver problems. Radio frequency interference. Okay, fundamental overload. If anyone has ever driven past a radio station and noticed that it doesn't matter what your radio is tuned to, that's what you hear. That's fundamental overload. You just basically can't resist that signal.
That's the same as when you're driving under high tension wires?
I guess, yeah. Yeah. Essentially it's generating noise. It's overload. It's not overload of a particular signal, but there's enough RF there that it just basically wipes everything out. Harmonics, a harmonic is an integer multiple of a frequency. So if I have a transmitter that's operating at 7, my first harmonic would be 7, the next one would be 14, then 21, then 28. And if you look at the frequency chart, you will notice that, what do you know? Let's take a look at those different frequencies that we have. We have 7 megahertz, and below that we have 3.5, and then 7, and then we skip over 10 because that was added later, but then 14, skip over this one here, 21, and then 28. Those are all harmonically related, which basically means that if we have a harmonic that is generated here, it will fall in one of the other ham bands, which is actually a fortunate thing. You still don't want it to happen, but at least it keeps us from interfering much with anybody else. And spurious emissions. Spurious emissions are frequencies, signals that are generated in a transmitter that are not related to anything else. Just happens to be randomly generated. If your neighbor tells you that you're interfering, well, the first thing is that you make sure that all your other stuff in your own house is not being interfered with, because who's got the license? You are a licensed station. If you are transmitting legally and everything is clean signal-wise, it is their fault, not your fault. There is something called Part 97. The amateur radio community follows Part 97 of the FCC rules. Everything else, laptops, iPads, cell phones, this coffee cup, if it puts out any kind of electronic signal or can be interfered with by anything else, it is a Part 15 device. Part 15 cannot interfere with any licensed service. Part 15 devices have to accept all interference from any other licensed service. So a TV would be under Part 15. If you're interfering with your radio, with your neighbor's TV, it's not your fault. You might want to help them fix it, but it's not your fault. Similarly, if they have a brand new TV and it's interfering with your radio, impeding your ability to operate and receive, they have to fix it. It's not your responsibility, it's their responsibility. Non-fiber optic TV, basically, if you have a connector that comes loose, it allows a leak of signal in and out. An AM or FM broadcast radio could receive a ham signal if that radio, because of the way it's designed, is just unable to reject a strong signal nearby. I used to be able to get onto, my parents could always tell when I was a kid when I was on the radio because they'd turn on the stereo and they'd hear. Similarly, even when the stereo was turned off, sometimes they would hear with the stereo turned completely off. So that would be inability to reject strong signals. How can fundamental overload of a non-amateur radio or TV receiver be eliminated? You can put a, look at that word, filter on the other receiver. If you put another filter on there, it'll block out certain frequencies. It used to be that the telephone company, which was the Bell system, if you, let's say, rented their equipment and you had a telephone hanging on the wall. Anyone remember telephones hanging on the wall that were plugged into the wall? If you had a ham radio and it was interfering with your phone, they would come out and they would put a filter on your phone for you because it was their phone. And because
before deregulation.
Yes. And before, well, and also before cordless phone. So because any piece of wire can function as what, everybody?
Antenna.
An antenna. So all that wiring in the wall circuitry that the telephone was connected to would make a wonderful antenna. There's also something called a band reject filter. We drew band pass filters. Those allow a certain amount of a certain range of frequencies to come through. If you flip it upside down, you can have a band reject filter so that it allows everything except a tiny little band of frequencies to get through. That's also known as a notch filter. So let's say you have a commercial FM station nearby and they are interfering with you.
Unknown caller.
They are interfering with you. You can build a notch filter which notches out their frequency so that it doesn't interfere with you. Something in your neighbor's house. Let's say your neighbor has a pot grow. This is Eugene, Oregon. Everybody's got pot grows, which means everybody's got grow lamps. Everybody's got grow lamps. Grow lamps put out a massive amount of light. They have massive switching transformers built in. They generate an enormous amount of RFI, or they don't, depending on where they bought them. Every grow lamp is supposed to not put out massive amounts of RFI. So if your neighbor who has a pot grow in their basement is putting out a massive amount of interference and it's interfering with your ability to operate a licensed station, who is at fault?
The neighbor.
The neighbor is at fault. So if you have a good relationship with your neighbor, you might walk over to your neighbor's house, which hopefully in Oregon, it's a legal pot grow, and say, hey, you know, those grow lamps that you have are interfering with me. You need to replace them. And if they don't fix it, you actually have a recourse. You can go to the FCC and file a complaint against that. If you have a neighbor who has an illegal pot grow, well, you might want to, you know, leave a note over there and say, by the way, your pot grow is causing me interference. You don't really want the police involved in this, do you? You might want to get new lamps. So anyway, This is actually
And
a
you might
very,
want to get a bulletproof vest.
yes. Well,
Yeah.
that's why you leave a note. But you know, this is actually a very real problem today. We have many pot grows here in Eugene, for instance, and some of the growers use approved lamps and some do not. And there are people for whom their entire frequency band is completely wiped out by those lamps.
And
So-
approved that you would, I assume, go buy that at a store as opposed to making your own.
Yes, yes.
Okay.
But ideally, but there are, and actually the manufacturers of those lamps are supposed to meet FCC requirements before they sell them.
Okay.
And they don't always, and that's a problem. Okay, if your audio signal through an FM repeater is distorted or unintelligible, you could be in a bad spot. You could have batteries that are running low. Your transmitter could be drifting off frequency. Either way, it's going to sound like you're distorted. RF feedback. RF feedback sounds very much like any other kind of distortion. Basically, it's if you're getting too close to your microphone, it sounds very similar to what feedback happens when it gets back into your microphone. If you are okay, if you are using a radio and somebody says, "Hey, we can barely hear you," well, okay, the way to fix that is you increase the microphone gain. Most handheld radios do not have a microphone gain control. We have the ability to do microphone gain. It's called this. We can take the radio and we can get it closer to our face. I've noticed, for instance, we have a net on Monday nights where people get to practice being on the radio, sometimes for the first time, sometimes for the millionth time. Anyway, what we've noticed is that some people, for some reason, this is their go-to position for holding a radio. Barely hear what they're saying. You say, okay, by the way, we got to get you used to close talking. Take the radio and put it right up to your face. And if it's too loud, we'll let you know. So that is our microphone gain control. Tell them to get the radio right up against their face. Using basic instruments and soldering. Okay, voltage and resistance. So does anyone here have a Harbor Freight near them? Anyone have Harbor
Yes.
Freight
Yeah.
tools?
We do.
Harbor Freight tools is great. I love Harbor Freight tools because it's the disposable tool for the tool that I don't care if I lose. Sometimes I just want a pry bar that I don't care if I break, right? But sometimes I do want something that is going to last forever. So the other thing is sometimes I want something that's going to allow me to do measurements and testing in a safe manner. So here's a Harbor Freight, for instance, not to focus on Harbor Freight. It's just that everybody has one of these. I have several of these. And the reason I have several of these, you may recognize this. It looks kind of like this. It's the $10 voltmeter. Sometimes I'll have a $5 voltmeter. Sometimes I'll have a 3 voltmeter, which works quite well. Does anybody own one of these? And they have it in a bag and they just toss it around. And if anything happens to it, it's great because it's $5, right? It works for measuring low voltages.
I use them all the time.
Exactly. Now,
And if you use this one right here, you can use too much voltage and burn them up too.
Ah, that's true. Now, one thing
Look at
that
the yellow.
is true about these is that you will see that on that scale, as you spin around, there's a 250 volt setting. I am very comfortable using that meter to measure 24 volts and maybe even 120 volts, but I am not going above that. The reason I'm not going above that is that I don't want to die, at least not in that way. So I have, for measuring higher voltages, something called this. Notice the other meter was $5. Notice how much my Fluke 87 is.
Wow.
$500. This is a multimeter that is rated for operation at 1,000 volts, and it's been tested as such. The probes are measured to be good at 1,000 volts. The circuit board will not blow up when I use it at 1,000 volts. This is what I use for work. When I suit up and I go and I test high voltage, 480, 500, 600 volts, this is what I use. This is very different, again, from the $5 multimeter. They look very similar. They measure the same thing, but they are built completely differently. And that's why it's important, if you're testing voltages, to do it in a safe manner. Okay, know your equipment. Okay, a multimeter measures voltage and resistance. To measure electric potential, again, that is EMF, electromotive force. That is a volt. So you would use a voltmeter to do that. To measure applied voltage, you would put it in parallel. Essentially, looking at a battery. If we're trying to measure the voltage on something, we do this. We want to see what the voltage, what the potential difference is. We would go like this with our voltmeter and measure the voltage in parallel with the power supply. If we had two resistors, for instance, and we wanted to measure the voltage drop across either resistor because we didn't know what they were, for instance, there's a resistor and there's a resistor. We could put a voltmeter across here, and we could put a voltmeter across this one. And we would measure the voltage or potential difference across either of those points. Now, if we wanted to take this circuit and we wanted to see what the current was, we would take an ammeter, because am for amps, and we would insert it in series. Here's our ammeter, so that it was measuring the total number of electrons flowing through the circuit. Now, there's another form of an ammeter called an inductive ammeter, which, as current is flowing through the wire, it measures the magnetic field generated by that current. That is an inductive ammeter because it uses the principle of induction, which is a current causing a magnetic field. It induces a current and a voltage in that coil, which we then measure using a voltmeter. And we indirectly get a current reading off of it. Typically, this kind of ammeter is used for very high currents. We don't use it because of sensitivity. We don't usually use that for very low currents.
And why is this drawing that you did in the answer parallel as opposed to serial?
For what? For a voltmeter?
Yeah, for measuring, well, I assume the question was measuring voltage.
Yes, for measuring voltage, you do it in parallel. The way that a voltmeter works is that it essentially has a galvanometer and a resistor. And by knowing how much current flows in a true meter, that would actually cause the galvanometer to swing a certain distance based on how much current flows through the resistor.
Maybe the question would better be, what would be the difference between measuring in parallel versus measuring in serial?
Well, what if you put it in series?
Yeah, I think
if you put a voltmeter in series, okay.
Yeah, remember we're a
Yep.
bunch of farmers, so we're not understanding this.
Okay, well, let's put it in series. Here's our voltmeter. Again, this has a meter in it and a tiny little resistor, and now a resistor here. Is that meter?
Oh, I see it. I see.
Is that meter designed to carry 5 amps? I don't think so. You know, that will cause it to smoke.
Okay. Yeah, I saw the difference there.
Similarly, if we were to do the same thing with an ammeter, here's our battery, and we take our circuit and do this with it, and we take our ammeter and put it in parallel. An ammeter is just basically literally a coil that drives a needle. If we were to expose that to the full force of the battery right here, what would happen to it?
Gonna.
Yeah, basically the battery would just run right through there, and you'd again cause a certain amount of smoke to come out of your meter. Okay, well, there's another kind of meter that we use called an ohm meter. And an ohm meter is a very special kind of meter because it measures a resistance. Now, what do you know about a resistance? Doesn't require any voltage or current, right? Resistance is a property of this device. We're not measuring a voltage. We're not measuring a resistance, but we do know Ohm's law. So we have our ohm meter, And our ohm meter includes a battery and an ammeter. So if we know our voltage, because we're the ones who bought the battery, and we know what the current is because we have a meter in there, we have our E and our I. What is the unknown here?
Oh,
That is what we're trying to measure. Well, we know our E and we know our I, therefore we can calculate R. That is what an ohm meter does. It has a power source and an ammeter built into it. But now the tricky thing is, let's say that we have a battery already hooked up to this circuit, and we try to measure something using an ohm meter. This will not work. What you need to do is break this wire so you can measure this device completely independent of the rest of the circuit. Otherwise, you will get very, very erratic readings. The other thing that can happen is, let's say that we take our ohm meter, which looks like this. It has an ammeter built into it. This is in a box. Okay. And we hook this up to an unknown circuit. And we see that the resistance starts off over time as 0, but then it goes up to infinity. This means that there's a capacitor in there because it's actually calculating based on the battery and the measured current. So if I have a DC battery, right, a DC power source, this is a capacitor. This charges up. At first, it takes a lot of current. A lot of current by Ohm's law is no resistance. But then once it's completely charged up, what happens? Do we get any more current flow? We do not. So we end up with infinity resistance. So if you see a curve that goes like this, where you have 0 resistance that goes up to infinity, it means you have a big capacitor in your circuit. And you're actually charging up a capacitor with your meter. Okay, let's see. What can damage a multimeter? Attempting to measure voltage when using the resistance setting, for obvious reasons. Resistance, it has a battery built into it. I have another way to blow something up is to hook it up when you're trying to measure voltage and hooking it up in the current setting. And then you end up replacing a fuse that's built into your meter. If there's no fuse built into your meter because it's a cheap meter, then you let all the smoke out and it never works again. When measuring high voltages, make sure that the voltmeter and leads are rated for the right voltage. Again, that's why I have the expensive meter for work. How is an ohm meter connected to measure its resistance? In parallel, make sure that the circuit is not powered. You have to disconnect things. What reading indicates that an ohm meter is connected across a large discharge capacitor? We just did that. Your resistance starts at 0 and goes up to infinity. To measure electric current is an ammeter. To measure current, you put it in series. Okay, and finally, different solders. Okay, we use something called electronic solder. There is lead-free solder, which is a little friendlier into the environment and to your health than leaded solder. Our typical solder is a resin core solder, not acid. Notice this says, what should you not use? Acid core solder is for plumbing. We do not do that here. Acid core solder will destroy your circuit board. So we typically use lead and tin or tin and copper. Those have low melting points. And we use rosin core, which is usually a tin lead combination. And the rosin is at the center of it, and it burns off and cleans off any oxidation. A cold solder joint. A cold solder joint is something that looks like it might be a good solder joint, but isn't. Essentially, what'll end up happening is that if all the components that you've tried to heat up and flow material together to, If it has not electrically connected, what you'll end up with is something that looks like there's a little bit of a gap. And invariably, on the day that you need it to work right, it won't. Because if the temperature goes up or down, or there's a little mechanical jolt, there's a mechanical connection, but not an electrical connection. And if it's not a nice smooth surface, there's probably not a good solder joint there. All right, we're now into operating procedures, FM. So if you're using a repeater station, how do you do that? You'd say, this is N7JI listening. A repeater station takes your signal and puts it in another place. It's an automatic process. There are different kinds of stations that can automatically retransmit the signals of other stations. They're known as a repeater station, basically listening and repeating something. A space station, which is anything 50 kilometers or higher up in the air. The ISS is a space station that actually has a repeater station on board. An auxiliary station is kind of like a backbone repeater, where let's say you have two mountaintops and you have one repeater that's talking to another repeater, or a system that's sending telemetry information from a water gauge to somewhere else. It's not really intended that it would ever be listening, so that's an auxiliary transmitter. Those are automatic. Those operate in automatic mode. A linked repeater network is something that connects multiple repeaters together, either by RF links or by internet linkages between one system and another, so that when you transmit into one repeater, your signal is retransmitted on 2, 4, 10. In Oregon, we have one that's 50 linked repeaters. So if you access any one of them, you're transmitted over 50 different repeaters around the state. A common frequency repeater frequency offset in the 2-meter band is plus or minus 600 kilohertz. On the 70 centimeter band, it's plus or minus 5 megahertz. CTCSS, also known as private line. Private line, or PL, is a Motorola trademark. CTCSS is that low frequency tone that is essentially the key for opening up a repeater's receiver and allowing you to get your signal transmitted into the world.
Quick question.
Yes.
The PL is analog. What's the digital version of PL?
It's DCS, digital code squelch. And
Okay,
that's
we don't deal with
yeah,
we don't deal with P25, so it's not
No.
it's not a P25.
correct. If you're unable to hear or access a repeater, you might be listening to you might have the wrong offset, you might have the wrong CTCSS tone, or you might have the wrong DCS tone, the DCS code. Okay, every handheld radio, every FM radio will have a button called reverse. On mine, it's kind of like wiped out, but that reverse button allows you to reverse your offset. Since you're normally listening to a repeater's output and transmitting on the repeater's input, the reverse button flips those temporarily. And that allows you to listen to people who might be transmitting on the wrong signal, on the wrong frequency. What would cause FM transmissions to be distorted? That would be too much audio. You're over deviating. When you transmit with an FM radio, the amount of bandwidth that you take up is called deviation. There's a deviation or modulation index. And if your radio is getting too much audio input, you will over deviate and your signal will extend beyond what the receiver is listening for. And then some of your signal will be missing. If some of your voice is missing, that sounds like distortion. How do you call through a repeater? Okay, do we have anyone licensed here yet? Yell out if you've got your license already. Who's got their license already?
Yeah, you betcha.
What's your call?
Almost.
What's your call?
It's yeah, I don't have it memorized, right?
What?
Yeah. KJ7TCG.
Okay, Kilo Julie 7 Kilo Juliet 7 Tango Charlie Golf. This is N7JI. Over. How would you answer?
I don't remember.
My call sign, then yours.
Just the opposite.
Right.
Go ahead. N7JI, this is?
N7JI, this is KJ7TCG, or, yeah.
Okay, that's it. So you basically give the other station's call sign, then your own.
Hey, Scott,
Which,
Yes.
something that we learned in pilot training when it comes to talking on the radio, which helps me with amateur radio, is always thinking, hey, you, it's me.
That's right. Exactly right. Other station always comes first. The other
So-
way to indicate that you're calling and listening is N7JI monitoring or N7JI listening. That
So
just
you
says,
wouldn't use
"I'm here."
you wouldn't use the
CQ.
instead of using N, you wouldn't use Nancy 7
Use
Juliet
it.
India.
You can use standard ITU phonetics. Now, sometimes some people will say, November 2 jumping jack. If it's colloquial, sure. But if you're using standard ITU phonetics that everybody will know, you learn the whole alphabet. Alpha, Bravo, Charlie, Delta, Echo, Foxtrot, et cetera, et cetera. If you happen to operate, if you're a police dispatcher, they have a different system. So just to make things complicated, then you have to memorize 2 different complete systems. If you're transmitting, if you and another person are transmitting on the same frequency, that is known as simplex. Why would you operate simplex? A repeater is a utility. A repeater is a resource. If you're within mutual communications range, you're only half a mile apart, and you don't need to use a repeater, and you don't need to talk to anybody else, you would just use simplex. The national simplex calling frequency that everybody seems to scan because it's the national simplex calling frequency. I have it programmed on every radio that I have. When I scan, it always goes through, is 146.520 megahertz. And I also scan 446.000. When I'm traveling on a long road trip, I always scan through that frequency. You'll meet other people on that frequency frequently. Okay, CQ, we're now on the high frequency bands. Everybody, what are the limits on the high frequency bands in megahertz? I told you I'd keep quizzing you. What are they?
300
300
to
to
300.
3,000.
You
What
said
was that
high
again?
frequency.
On high frequency.
High frequency.
HF,
3 to 300.
3 to 30 megahertz.
Yep.
I mean, 3 to 30, right?
3 to 30. Okay. So if you're on the high frequency bands, we don't usually have repeaters. Since we don't have repeaters, we're calling into the great unknown. When we're calling into the great unknown, we're basically saying, okay, I don't know if anyone's there. I'm going to seek somebody. CQ, CQ, CQ. CQ means I'm listening for anyone. You would not use that on a repeater because you know that there's a repeater there. This is only if you're calling and you're not expecting anything to respond, potentially. So CQ, CQ, CQ. This is N7JI. Before you call CQ, you always make sure that you're allowed to be transmitting on that frequency. You have to know what your privileges are. Then you listen to make sure that there's nobody on the frequency, and then you ask if the frequency is actually busy. And the reason you would have to ask is because somebody else may be listening on that frequency to another station that you can't hear. And by suddenly calling on that frequency, if you start calling CQ, you might actually be interfering with somebody else. So you ask very quickly, is this frequency in use? In Morse code, we would say QRL question mark. QRL question mark means, is this frequency in use? Okay, let's say you hear somebody calling CQ. CQ, CQ, CQ. Mr. Omo, would you like to answer me here? CQ, CQ. This is November 7, Juliet, India calling CQ and listening.
Let's see, November 7, J1. This is KJ7TCG.
Okay, thank you. You just called me. KJ7TCG, this is N7JI. Thanks for the call. My name is Scott, and you're a good solid 5N9. How are you today? Over.
This is KJ7TCG. It's a beautiful day, and I'm learning something.
You have to give it back
Scott,
to me.
question on that.
Yep.
Does he have to answer with his call sign? Once
Okay.
you've established who's there.
Okay, the rules state that you have to give your call sign every 10 minutes and at the end of communication. There's no rule that says you have to do it at the beginning, although most people do. And then within the conversation, it has to be every 10 minutes. That's it.
Okay.
Those are the only
Or
rules.
at the end of your statement?
Or at the end of communication. So in other words,
Okay,
like
gotcha.
your overall conversation is over.
Fair enough. So like after you guys identify each other, it's just conversational at that point.
Yep.
Unless 10 minutes or you're done.
Mm-hmm.
Cool.
And notice that he actually does not even, let's say we know each other, he doesn't even have to use his call sign to start in the first place. If I know who it is, you say, hey, Scott, hey, Mike, and we just start talking. And sometime we identify to follow the rules.
Now, at what point do vanity call signs come into
Yeah,
play?
we're getting to that. We're getting to
Okay.
that.
Fair enough.
Okay. So it's important to identify your station when performing tests. When you're doing a test transmission, the easiest way to do it is say November 7, Juliet, India, or whatever your call sign is. That identifies your test transmission and you're done. You cannot make a test transmission without an identification. QRM, we use Q signals a lot. Q signals are basically shorthand. There are only two that you would have to know for this exam. Although if you get on the air, you will find that people use a lot of different ones. QSY means I'm changing frequency. QRM means I am getting interfered with. A band plan is a voluntary guideline for using different modes or activities within an amateur band. So it is appropriate that we show this band plan right here. And so the rules state, for the most part, that we are allowed to transmit, let's say, on the 17-meter band from 18068 to 18168. That is the rules, that we have an allocation that covers the whole thing. Now, within there is a band plan. Notice that the red area on the left-hand side says CW/data, CW Ridian data. And on the right-hand side, we have the yellow, orange, and blue. And we look at yellow, orange, and blue, and that's extra class voice, advanced class voice, and general class voice. Those are the band plan. That is voluntary guidelines that are set up to keep the peace. Those do not necessarily, those are not necessarily the same from country to country. The rules regarding the band itself typically are, but how the band is used is not necessarily the same from place to place. Okay, so that's, again, a voluntary guideline. Which of the following applies when two stations transmitting on the same frequency interfere with each other? Nobody owns a frequency. Even if they're pissing you off, you have to figure it out. Public service and MCOM. A lot of people here may be interested in MCOM. There is something called ARES and there is something called RACES. They both contain within them Amateur Radio Emergency Service. These are two organizations that are set up to provide emergency communications to the rest of the world in case of emergencies. We are very good at this. We know what we're doing. We know how to use our equipment. We have frequency allocations that allow us to get lots of data across when other things go haywire. We are also trained. You know, we know how to do things. We know how to build stuff. We know how to build antennas. We understand what cables are and how they work because we've been trained. That's what we like to do. So Amateur Radio Emergency Service is ARES. That's a voluntary organization that you basically register qualifications and equipment. Now, the difference is between that and RACES is that letter C, which is civil. Okay, so in order to be a part of RACES, that means you actually register with a government organization or civil defense organization to participate. So ARES is a voluntary service. RACES is a voluntary service that is run by a civil defense organization.
And these were useful at the holiday fire, weren't they?
Oh yeah. Yeah, and earthquakes, tornadoes, hurricanes, getting help from one place to another. And we actually do a lot of practice drills.
Who is Aries registered with?
Aries is an ARRL function. Okay, so good opportunity to bring up what ARRL is. ARRL is our National Organization of Amateur Radio. So the FCC administers ham radio in the United States. Beyond that, there is essentially like a member organization of which about 160,000 American ham radio operators belong, that essentially is our kind of like conduit and lobbying organization that talks on behalf of all of us to the FCC and to Congress. In addition to that, they do other things as far as, for instance, awards, training, providing various different services such as QSL bureaus and stuff like that. Legal counsel, engineering counsel. They run a laboratory, an RFI laboratory, code practice, lots of other things. Anyway, I guess I should say that I'm a strong believer in clubs. I'm a strong believer in an organization like the ARRL, and strong enough to the point where I have actually volunteered to be the Oregon section manager. So basically, I'm kind of like the Oregon state representative for the field services group that is responsible for providing whatever services and being the conduit between the state of Oregon and its 4,000 members and the national organization.
If anybody is going to be in Connecticut, especially the central region just south, call a day ahead of time to see if there's somebody that can give you a tour, take you through the museum, or to see into the lab. We have Senator Blumenthal, which is working now. I said yesterday he's working with the ARRL to try and get homeowners and homeowners associations and apartment complexes be allowed to.
Because it's an emergency thing, right? The argument is that it's for emergencies. We need to be able to operate wherever, whenever, when the time comes, and it doesn't behoove anyone to restrict it. It may not like the way it looks, but okay. There's a lot of things that people do that you don't like the way it looks, right? So, Rich, where do you live? Uh-oh. Everybody still here okay?
Yeah, I can hear you.
Yeah,
I can hear just fine.
Okay.
yeah.
So we were talking about ARRL. So this is ARRL. It's the National Organization for Ham Radio. It's the membership is $60 a year, and we, as he was saying, Senator Blumenthal, the ARRL works very closely with Congress because FCC rules and stuff don't get changed without an act of Congress. So there are numerous, we have a lot of people lobbying on Capitol Hill to get us what we need, to get the ear of the FCC. In addition to that, notice we have all the news and views and lots of other stuff as far as, for instance, if you happen to see the fact that this class was happening, there's a fair chance that you saw it on ARRL's website. They maintain a list of all the clubs in your area. They maintain a list of all the classes that are occurring wherever they happen to be. Publish numerous different magazines and books and stuff like that. So a very worthwhile organization. I'm a strong supporter. I strongly recommend you consider joining when you get licensed. Anyway, that's my advertisement. Let's see. Back to
Scott. Did everybody hear me, or did was my mic off?
We heard most of it. I think we heard about Senator Blumenthal and the battle with and the battle against homeowners associations and um, apartment landlords.
Yeah, if you get a chance, if you're in Newington, go up and if you have a day, if you can call a day ahead, see if somebody's there to give you a tour of the facility,
Yeah,
of the
and, you know,
museum.
I the last time I was in Newington was 30 years ago, but I went by and I actually got to sit and operate. That's the thing. The W1AW is the ARRL station. If you have a license, you can actually operate. And it's a very, very, very popular call sign. It's quite the rush for somebody who's really interested in ham radio. Okay, let's see. Net control. A net is short for network. A network is a group of people who are talking together using a certain protocol at a certain time and frequency, and the net control operator is the one who is in charge. And the way that a net works is I'm starting a net. Okay, anybody would like to check in, please stay checked in until it's time to check out. If you need to go, let me know. So basically, net control is kind of like the traffic cop. If you're in a net, you don't say anything unless there's an emergency or unless net control asks you to say something. Traffic in a net is messages exchanged by net stations. If you're talking about cooking, well, it might be that we need a half dozen hot dogs. That is traffic. If you're talking about health and welfare traffic, it could be that somebody just gave me a phone number and a name and an address and would like me to let somebody else know that they're okay. That would be health and welfare traffic. In order to eliminate ambiguity, you would use something called the phonetic alphabet. Again, the ITU standard phonetic alphabet, Alpha, Bravo, Charlie, Delta. We spell out things, for instance, Trujillo, Tango, Romeo, Uniform, Juliet, India, Lima, Lima, Oscar. In case there's any ambiguity, somebody might not know how to spell it, I'm going to spell it out using phonetics so that it's understood unambiguously. The preamble of a formal message contains information needed to track it as it passes through the system from person to person or from computer to computer. The check in a radiogram is quite literally a text message written on a piece of paper or on a computer. The check is the number of words or word equivalents. If the message is, I will meet you at the zoo, 1, 2, 3, 4, 5, 6, 7. It will say, I will meet you at the zoo, check 7. So if somebody said, I will meet, if they heard whatever the message was, and they heard a check of 7 and their word count did not add up, that means they missed something. And they would then ask for a repeat. When do FCC rules not apply? The answer is they always apply. When are you allowed to go outside of your outside of your frequency allocations? There's these two things that always come up: immediate safety of human life or protection of property. If those things happen, immediate safety of human life or protection of property, the rules go out the window, and you could use whatever means are at hand to get a message across. That means if you have a cell phone, you should use it. But if you can't get a cell signal and you have a handheld radio, but you don't have a license yet, or you have an HF radio available to you and you hear somebody talking, but you only have a technician license, that means go ahead and do it. You might have to explain later why nothing else worked, but go ahead and do it if it's truly an emergency. Okay, how about a 5-minute break, everyone?
Yep, that sounds good.
Okay. And we're on to amateur satellite. So we're really into the rules and regulations now. Doesn't that sound like fun?
My favorite.
Yep. Okay. See y'all in 5 minutes. Okay, everybody ready for the home stretch?
Yep.
How's everybody feeling? It's the home stretch.
Ready.
This is all the rules and regs that you have to go over. And most of them are common sense. There's a little new terminology, but most of them are common sense. Okay, amateur satellites. We are allowed to build and launch our own satellites. Any amateur holding a technician class license or higher can contact the ISS on the VHF bands. That has nothing to do with the ISS. That has everything to do with the VHF bands because a technician can operate on VHF. Operating in UV mode, that's uplink, downlink. So U is UHF, V is VHF, uplink on UHF, which is 70 centimeters in this case, downlink on the 2-meter band. The mode of transmissions that are commonly used by satellites, single sideband, yes. CW, yes. Data, yes. FM, yes. The impact of using excessive radiated power on a satellite uplink, essentially, imagine you're on a satellite 200 something miles up or 10,000 miles up or whatever it happens to be, and you're looking down at a lot of the Earth. One strong signal is going to obliterate your ability to hear everybody else. So if you have too much effective radiated power on an uplink, you block access by everybody else. If you, a satellite will typically send out a beacon, beep, 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 sometimes with a call sign, sometimes with other information indicating how the satellite is doing. Now, we're literally talking a satellite that could be as big as a small house or something that is 4 by 4 by 4 inches floating around. That's known as a CubeSat. That's a 1U CubeSat. It's just basically a block floating around in space. So depending on how it's built, it will be sending out information. It could be a call sign. It could be the weather up there, you know, what its temperature is, what its orientation is, what the battery charge is. This is sent down as part of a beacon. Your signal strength, when you're listening, you could hear yourself. Your signal strength should be about as strong as the beacon signal. LEO is LEO, which stands for low Earth orbit. LEO. That's a LEO satellite. That is different from a geosynchronous satellite, which stays in one place above the Earth the entire time. A satellite that is geosynchronous can typically see an entire hemisphere. A LEO satellite, or low Earth orbit, typically moves around the Earth very, very quickly. So like the International Space Station makes one orbit of Earth about every 90 minutes. So it doesn't quite see the entire footprint. And to go from horizon to horizon is about 10 minutes. A beacon is a satellite, is information from a satellite containing information about the satellite. Again, health and status of the satellite is sent in satellite beacons, and anybody can receive telemetry from a satellite. So if you think about the word telemetry, tele meaning distance, metry meaning measurement. So long distance measurements. You're asking for just information about what the satellite is doing. A satellite tracking program. A satellite tracking program is a piece of software, sometimes on the web, sometimes standalone, that uses something called Keplerian elements. These were developed by Johannes Kepler to define what an orbit looks like. You punch those into a satellite tracking program, and it tells you where the satellite is, when it's going to make a pass. And because satellites are the low Earth ones are going to be moving quickly with respect to you, we actually have to deal with Doppler shift, the same way that a fire truck or a race car or something going by sounds like a satellite as it approaches you and goes past you. Its apparent frequency of operation will actually change. It is moving fast enough, even though it's transmitting things that are moving at the speed of light, to actually shift the frequency. So when the satellite is approaching you, like this, and you're down here on the ground, and it's transmitting on 437.800, you will actually hear it at 437.815, 810, and 805 as it gets closer, and the speed changes. And as it goes away, you'll actually hear it transmitting on 437.795, 790, 785. Consequently, because it's coming toward you, you actually have to transmit at a lower frequency when it's over here and a higher frequency when it's on the right, because the signals get stretched out. This is a real world impact. How many of you have ever heard of Doppler shift with regard to radio waves? This is Doppler shift with regard to radio waves, and we deal with it all the time when we're trying to work through a satellite. In my car, I actually have all of these frequencies programmed on my mobile radio so that when the International Space Station passes overhead, I can continually tune and change frequencies and hear it as it makes its pass. Okay, next one. Doppler shift. Okay, spin fading. Satellites rotate and tumble as they travel through space. That's how they stay stable. Their antennas are at a particular spot. Those antennas may or may not be where you expect them to be. So their signal to you might fade in and out as it spins. Operating activities. Okay. One of my favorite activities, radio sport. When you're out trying to make contact during a given period of time, making as many contacts as possible, that is known as contesting. That's a contest. Every contest has its specific exchange of information that's necessary. When we just sit and chat on the air, that's known as rag chewing. Contesting is very different from rag chewing. If the exchange is your name and your state, and unless I know somebody really well and want to spend time with them, I would just basically say, KJ7TCG N7JI, Scott in Oregon. And the reply would be with call sign, name, state. And I'd say, okay, thank you. Who's next? Because the goal of a contest is to make as many contacts in a certain period of time. The longer I take, the fewer contacts I can make. A grid locator. One of the things that I sent out as part of the packet is a grid square map. And let's see if it comes up. Hey, can everybody see that? There's a grid square map of the United States. It gets into Canada, gets into Mexico. The rest of the world is actually laid out in these grid squares as well. Each big square, letter, is 20 degrees in latitude by 10 degrees in longitude. No, sorry, 10 degrees. Yeah, 10 degrees in latitude by 20 degrees in longitude. So north-south is every 10 degrees, 20 degrees in longitude. And within each one of those grid square, the big blocks, is a 10 by 10 matrix from 00 to 99. So what that allows us to do is more accurately pinpoint where somebody is on the globe. So for instance, I am in CN84. I'm also in Oregon, but notice that in Oregon, I could be a lot of different places. This allows me to, if I'm talking to, let's say, somebody in Idaho, DM Delta November 18, that would be Northern Idaho, versus Idaho DN 12, I would follow a very different beam heading to get there from CN84. So knowing where they are just gives me a little more accuracy as far as pointing an antenna. We also do radio direction finding. These are known as fox hunts. We call them bunny hunts or duck hunts here in Eugene. Basically, you hide a transmitter somewhere and tell everybody to go find it. You use a directional antenna, you use a handheld radio, and you walk around or drive around and try to find the hidden transmitter. This is really good for picking up sources of interference as well. Good practice. Internet Radio Linking Project, or IRLP. This is This is basically a system by which repeaters and individual stations can connect to the internet and talk to each other using VoIP, which is voice over internet. Actually, when you make a phone call, it uses voice over internet. So essentially, if you think of it this way, your voice, which is analog, is digitized and then sent in packets over the internet to somewhere else. This is exactly what we do when we talk using VoIP and using the IRLP, Internet Radio Linking Project. Echolink, I use Echolink all the time. Echolink is an interesting system because once you have a license, you can install something on your phone called Echolink. Echolink allows you to call up different repeaters using your phone, using either a Wi-Fi signal or using a cellular signal, and connect to distant repeaters. The point of which is, let's say that, like I was in Austria, I wanted to participate in my club's net here in Eugene. Our club repeater is connected to the internet, and it has an Echolink address. So all I had to do from my hotel in Austria at 3 in the morning was wake up at 3 in the morning, get on my phone or my computer and connect using Echolink to my club repeater and participate in our net, in our weekly net. Nice little remote tool. Not exactly radio, but a kind of a radio internet hybrid. In order to use Echolink, you register your call sign and provide proof of your license, just a copy of your license. Using IRLP, Internet Radio Linking Project, you use DTMF. Okay, you will see as soon as you get a handheld radio, I am sure that it has a keypad on it, right? This keypad, for those of you who have ever made a phone call, of which there are probably many of you, will actually send out touch tones. If you are keying down the radio and you hit those buttons, it will send out touch tones. Those touch tones will be transmitted over the air and be received by a repeater system, which will allow you to open up a link. Once you've done that, you are now accessing the internet using that radio. That's known as DTMF, is dual tone multi-frequency. It's a pair of audio tones, thus dual tone, DT. An amateur station that connects other amateur stations to the internet is known as a gateway. Okay, now we're into part 97. Okay, so part 97, if you are curious about part 97, there's a copy of the part 97 rules which govern amateur radio maintained by the FCC. It's part of the Code of Federal Regulations, which is the law of the land. There's also a copy of it maintained by the ARRL. You can download a copy of it, keep it on your computer. You can refer to it. It's hundreds of pages long. If you ever really wanted to know exactly what the rules say, you go back to the Part 97 rules. The FCC is responsible for amateur radio in the United States. The basis and purpose of the amateur service. So what we're going to do is we're going to go to those rules really quickly. And we're going to go to Part 97. I'm going to unshare this, and I'm going to go to the FCC's copy of Part 97 text. Okay, Part 97. Here we go. A copy of Part 97 is maintained here, right there. Okay, here we go. These are all the rules. If you really feel like reading through them all, you can do a search on it. You can actually just look for whatever you want. However, the most important thing is right at the beginning, right here, basis and purpose. These 5 parts, Part A through Part E, are the reason why amateur radio, as a free service, we don't pay for access to our frequencies where everybody else does. These are the reasons that we are allowed to exist. If we fail at any of these, we risk losing our service. Amateur radio could go away. So we have to make sure that we continue to do these things. And so international goodwill, that's a good one. Expansion of the existing reservoir of trained operators, technicians, and electronics experts. We are not an appliance operators group. We are a group of people that knows what they're doing. As part of knowing what they're doing, knowing what we're doing, we are expanding the existing reservoir. We're keeping our country's technology infrastructure happy. We're keeping essentially the brain trust active. Encouraging and improving the amateur service through rules which provide for advancing skills in the communication and technical phases of the art. Now, you may think that everything that could ever be developed with regard to radio has already been developed. 10 years ago, there was no such thing as FT8. FT8 came about and is now used by about 70% of hams that use HF. It is a valuable tool for propagation studies. It's a valuable tool for learning about electronics and computer interfacing and for just making contacts. 10 years ago, that didn't exist. That is an enhancement that has been made. The only reason that we are allowed to use it is because somebody came up with it. And because they gave it to everybody, it's not secret. If it's not secret, everybody has the decode key, you're allowed to use it. We're not allowed to encrypt anything unless it's, specifically for like a satellite or a radio controlled craft. Advancement of the radio art. Single sideband started on the ham band. Before that, there was only AM radio. This was a huge change in the 1950s. And value of the amateur service to the public as a voluntary, non-commercial communication service. That is why we don't pay anything, but in particularly with regard to emergency communications, when something happens, we are expected to use what we know and the equipment that we have for the public good. So that's the reason we exist. Okay, definition of a beacon. This is any station transmitting for the purposes of observing propagation or experimental activities. Part 97, a space station is any amateur station that is 50 kilometers above the Earth's surface or higher. Willful interference. This means that somebody is annoying me and I'm going to interfere with them so that they don't have fun anymore. We are never allowed to do this. We have a tuning knob. We should exercise the discretion of turning the tuning knob and going somewhere else. There are a lot of other different frequencies there. There is something called a volunteer frequency coordinator. We have on the amateur bands, we have where does it go? Band plan. Okay, so here's our band plan. We're going to go to the 2-meter band. Notice on the 2-meter band, it just says in this orange area, it says FM repeater. Does it say who uses the repeater's frequencies? Does it say who gets to do it? It does not. So the FM, so that right there basically says that there is no specific rule that says who gets to use a repeater frequency or a repeater. It just says that's a repeater frequency. The volunteer frequency coordinator is the one who deals with all the arguments and all of the access stuff. Somebody wants to put up a repeater. Oh, well, there are no frequencies available. Or, well, we could move this one to somewhere else so long as they're okay with it. Or, oh, I think that repeater's been down for 3 years. That frequency hasn't been used at all. We're going to tell them that they don't have that frequency anymore and we're reallocating it to you. So a volunteer frequency coordinator is somebody in a certain area that has volunteered to handle those disputes. That person is selected by stations in a particular area that are eligible because they have licenses and are able to put up repeaters. They trust a person to make those decisions for everybody. In Oregon, that's called the Oregon Region Relay Council, or ORRC. Every state has its own board. Okay, frequency spectrum charts. This is really important to know. There is no other way to do this stuff other than memorizing it. And so here's the frequency spectrum chart. The first question is, what band, what is in the 6 meter band? Well, okay, there's only one way to do it. Look at the 6 meter band. It goes from 50 to 54. Therefore, the answer is 52.525. Now, if you go through your math, 49 is closer to 6 meters exactly, but that is not the answer. And the reason it's not is because it's approximate. Anyway, the 6 meter band covers from 50 to 54. It's just stuff you have to memorize. On which bands does a technician class operator have phone privileges? We go here, we look at the 10 meter band, we see that blue hash mark, we see novice technician voice. Voice is the same as phone or telephony, which means that a technician class operator can operate on 10 meters from 28.3 to 28.5. And what do you know? There it is, the 10 meter band. And you have access to 28.3 to 28.5. This is just stuff you have to memorize. Now, let's say that you are on 28.5, that you are on this, in this segment right here, you're on 10 meters. What is the highest dial frequency you can tune to if you're using upper sideband? Okay, again, this is another reason why we are in class. Okay, so 28,300 to 28,500. This is where the rubber meets the road, everybody. Let's see if everybody's been listening. So here's our carrier frequency. That's our dial frequency. And we are on upper sideband. Our signal is going to be on the right-hand side. Okay. What's the only rule? What frequency can you tune to? And what are the rules as far as the highest frequency you can go? The only rule is that your entire signal has to be between 28.3 and 28.5, which means that how wide is that signal? Everyone? How many kilohertz?
200
30?
kilohertz.
Upper sideband is 3 kilohertz wide. In order to make sure that this entire signal stays inside the band, we're going to draw it right here. How wide is that signal again? 3 kilohertz wide. This is 28.5 megahertz, which is 28,500 kilohertz. That being said, what's the highest dial frequency you can have and still have this be legal?
28,497.
That's right. That's it. 28.497. Because if you go any higher than that, your signal will drop outside of your privileges. If I tune down to the lower end, I don't have that problem because I'm on upper sideband. This is where it's important to understand how radio works, which is that the fact that you got that answer right is a really good thing. So good job.
3 kilohertz is the bandwidth.
That's the bandwidth of a single sideband signal. And your entire signal has to fall inside your privileges. Your privileges go from 28.3 to 28.5. Those are the walls. Which means that if you tuned up any higher in frequency than 497, your signal would fall outside the band that you're legally allowed to be in.
But, you know, on the test, why can't they just put the 28,400, 28,497? Why they have to put 28,500?
Well,
You know?
Because which of the following frequency ranges are available for phone operation? What if you switch to lower sideband?
Oh,
Right?
that's different.
They don't tell you what mode you have to operate.
Okay.
That's why we have, again, we have so much flexibility. That's why it goes beyond that. There's no saying you have to use this mode in this place on this channel. You know, we have infinite flexibility. How many frequencies? Okay, let's ask this question. How many frequencies are there between 28.3 and 28.500?
Wow.
How many?
Infinite?
The answer is infinity. Yeah. There's
Infinity.
because if you pick two, you can always go smaller. If you pick two of those, you can always get, you know, a smaller space in between. We don't have channels. We have ranges that we can operate in. We have frequency bands. This is unique in as far as most services go.
Okay, but it's also depend on your equipment.
Not really. I mean, yeah, you can select it, but if you pick a channel 28, let's say you go to 28.325.006, you could switch to 28.325.005, but there's still space in between there. If you could go smaller, you could go in between there.
Oh, I see. I see.
And those are all valid choices. In other words, we have access to the entire band to use as we want.
Wow.
Okay, where can single sideband be used in amateur bands above 50 megahertz? We're just going to go over here and we will see that we will see SSB. Notice that we have that light green in every band. We always have a section of every band where it's been set aside for that. CW only, which are the red sections. Notice that there is on 6 meters and on 2 meters and on 1.25 meters, which is 222 as we call it, or 220. There's a little section of CW only. Here we go. Why should you not set your transmit frequency to be exactly at the edge of a band or subband? Because your frequency might not be the frequency you think it is. You don't want to fall outside. It all comes down to falling outside. Secondary services. So we are on, for instance, on the 60 meter band, we are not primary. We are secondary. The military is primary. On the 70 centimeter band, this whole band, 30 megahertz wide, we are secondary to the military. If they decide they need to use it, they can kick us off. The primary user gets first crack. So if we are not primary and there's somebody else there, we can't interfere with them. If we're primary, they can't interfere with us. They're not allowed to. Okay, except for some restrictions, our power limit is 1500 watts. On the high frequency band segments, as a technician, your limit is 200 watts, which is still gobs and gobs of power. Okay, from the FCC, you can get 3 different licenses now. There are still a novice and an advanced, which you can no longer get. You can get a technician, a general, and an amateur extra. No, I don't know why it's called amateur extra and just not extra. A license grant is good for 10 years. You can operate as soon as your license grant appears in the license database online. This is different from the way it used to be. When I got my license back in 1984, I passed my test. They told me I passed. I then had to wait for over a month while the FCC processed my license. I couldn't do anything. I just knew that eventually it would show up, and I was checking the mailbox every damn day. How many
So as a question, can we go back to novice? I mean, I see a lot of novice, but they don't exist. What, novice got changed into?
No, novice is still novice. You just can't get one now. But if you
Why is
have
that?
one, you can keep renewing it.
Keep renewing them. Okay, but why can't I get one? I don't understand.
They don't.
What's going on?
The testing requirements for it don't exist anymore.
Okay.
So it's impossible to get a novice license.
All right.
How many operator and primary station grants can be held by one person? The answer is 1. I can hold my call sign, and that's it. How do you know that a license grant exists? If it appears in the FCC ULS, which is the Universal Licensing System. If you went and got your FRN number, you got it from the ULS database. That is where your license will be held. The FCC does not even mail anything anymore. So if it appears in the database, you can print out a copy. You can get an official copy from the database. They will not mail anything to you. So don't expect to see anything in your mailbox. Vanity call signs. Okay. Any licensed ham can participate in the vanity call sign program. You have to select a vanity call sign that is appropriate for your call sign class, your license class, and also appropriate for United States rules. I'm on a couple of Facebook groups, and somebody posted that he wanted this call sign. It's a good time to do this. He applied for and didn't understand why the FCC did not allow him to get this call sign.
Billy.
B1 LLY. Well, the reason being that the United States in the table of allocations of prefixes around the world has been allocated W, N, K, and AA through AL. And apparently he did not remember that from his examination, and he requested B1 LLY. We know for a fact, if we look at the table, that B1 is allocated to the country of China. So the FCC rejected it and said, we have no ability to grant you that call sign. So any call sign that you request has to start with WNK or AA through AL. Period.
No, that's, we're talking vanity, meaning you kind of request your own.
Yep. So
but otherwise you're just assigned one.
Otherwise you're just assigned a sequential call sign. I requested N7JI. The format of this call sign is a 1x2. Every call sign has one number in it. And it is initially, when you get your sequential call sign, it will be tied to the area of the United States in which you live. The number 1 relates to the number of letters before the number. The second number relates to the number of letters after the number. This is extra class only, a 1x2. 2x1 is extra class only. So for instance, NK7Z, that's my friend Dave. I could also request a 1x3, which is like W3ABC. One interesting thing is when you're requesting a vanity call sign, your mailing address does not have to match the number in the call sign. So if I lived in California and I which is six call area, I found a 3 call that I liked. It might be confusing, but I could request a 3 call. This is available to all technicians and generals. Also, a 2x3 call sign is it can be applied for by a technician or a general. KA1AMT. Something like that. A 2x2 call sign can only be requested up here, or by an advanced class call sign. And again, there are no new advanced class call signs, so I don't think that's really happening. But like KA1MM, that would only be, practically speaking, be able to be applied for by an extra.
Scott.
Yes.
When you go from technician to general, does your call sign change?
Only if you want it to.
Okay.
Okay, let's see. Any amateur can apply for a vanity call sign. Which of the following is a technician class call? KF1XXX, that's a 2x3. That would be a valid call. If your license expires, it stays in grace for 2 years. If you re-up it, then it comes back. However, when it's expired, you are not allowed to use it. Right? If you have to wait for it to be active again. Yes.
Can you differentiate a technician class versus general just from the call sign?
No. You cannot.
Okay.
They have the same call sign group. A club consists of 4 members, so 4 officers essentially. If the FCC can't reach you by email, they can revoke your license.
Yeah. Well, can the FCC give you the call sign instead of making one?
Well, I mean, your initial call sign is sequential. I mean, it's random based on where they've gotten to.
Oh, okay.
So what? Do you want like a random W call? No, they won't do that. Authorized and prohibited transmissions. We're not allowed to do anything obscene or indecent. You know what is obscene and indecent. I don't have to tell you. If you wouldn't say it to a 5-year-old, don't say it over the air. Under what conditions is an amateur station authorized to transmit music? Now, if I were to say happy birthday, that's not really music, but music is like, like a broadcast station transmitting music. We are not allowed to do that because that is the job of radio station. However, this rule exists because in the 1980s, space shuttle rebroadcasts used to be retransmitted over the ham bands, and they would wake up astronauts with wake up music, which was actually music. So it is only allowed for retransmission of manned spacecraft communications if it's incidental, waking astronauts up. You never hear it anymore, but it's in the rules. Transmitting messages encoded to obscure meaning. We are allowed to use radio teletype. We're allowed to use Morse code. Those use codes. However, those codes are, the decryption keys are well known and public domain. Those are not considered encrypted. They are encoded. When are we allowed to transmit messages actually intended to obscure their meaning? And there's only one time, right? Even if you speak in a private language with someone, you are not allowed to do that. If words have a meaning that you're not planning them to have, that no one else will know, you're not allowed to do that. We speak in plain English, and we speak what we actually intend to get across. The only time you're allowed to do that is if you're running if you're controlling a space station like a satellite, or you have an RC craft like an airplane, and if somebody else takes it over, they can crash it. So that's the only time we're allowed to encrypt anything where nobody else knows what it says. The FCC is a member organization of the International Telecommunications Union. The ITU is part of the UN and handles international things between countries with regard to their communication. So if a foreign country has said that we don't want any American hams talking with our hams, they will get information from the ITU to the FCC. The FCC will say, here's a notice for all hams. You can't talk to anybody in Lesotho. You can't talk to anybody in Oman. You can't talk to anyone in Russia, whatever that happens to be. At present, there is, believe it or not, including North Korea, nobody that we are not allowed to talk to. We are allowed to talk to any other hams that we hear. There are no hams in North Korea. We are eagerly waiting and have been for many, many years for a ham to pop up in North Korea. That will be a very, very busy person if that happens. Wants to talk, everybody in the world will want to talk to them. It'll be chaos. When can you receive money for operating a ham station? Well, we're not allowed to receive money unless you are a teacher and you're teaching and using ham radio as part of your educational instruction. So I am getting paid a salary and I'm showing somebody what it means to be on the air. I'm operating a station and at the same time, I'm still getting paid. Now, if somebody, let's say you're volunteering, they want to bring you a pizza because you're hungry. Yeah, okay, that's probably okay. You can eat. So when can amateur radio operators use their station to notify other amateurs of the availability of equipment for sale or trade? Okay, you can't run a business on the air using ham radio. However, if you are, let's say, participating in a swap net and say, I want to sell my Yaesu FT60, I want $125 for it. Please contact me via email or on this net. That's perfectly fine. Now, if you showed up every week with 100 radios to sell, that's probably a business. But if it's incidental once in a while, that's okay. If it has something to do with radio. If I'm selling a computer desk for use in a station, probably okay. If I'm selling a blender for making smoothies in a station, maybe not. Broadcasting is information designed for the general public. We do not, for the most part, broadcast. We transmit. So you can forget the term broadcasting because we don't do it. When are we allowed to do one-way transmissions? When it is not broadcasting. So a one-way transmission is like a Morse code practice thing or an informational bulletin that we're sending out or telemetry data from a rain gauge or something like that. That would be one-way transmission. We are not allowed to broadcast. We don't broadcast. However, we can support broadcasters if no other means of communications is necessary and you are standing with a reporter, for instance, who has to get this message back to their news desk that this dam is about to burst. Well, would you say that's immediate safety of human life and protection of property? If there's a dam that's about to burst, go for it. So you can support broadcasting in that regard. You can use your radio to take care of that. So what are we allowed to do? Communications incidental to the purposes of the amateur radio service. And how many purposes are there? We looked at that list. There are 5 purposes that are enumerated in the rules. So if it is incidental to the purposes of the service and remarks of a personal character. I used to laugh when I used to hear old people, because I was 15 years old, talking about having to go to the doctor and how their sciatica was acting up. And, I can't wait to retire so I can play with the grandkids. And here I am 15 years old. And now here I am 55 years old. And guess what we talk about when we get on the air? Just take a guess. My sciatica is acting up because I have sciatica and I do have a doctor's appointment coming up. And man, I got like 10 years till I retire and my kid's graduating college. I have, it's interesting because 40 years ago, I got to see what I would be 40 years later. I had the benefit of being able to see that. When may an amateur station transmit without a control operator? The answer is never. The control operator is the person who is responsible for what is being transmitted. The station licensee is the person who is responsible for the equipment itself. So the station licensee designates a station control operator. So there's actually 2 pieces to a license. There's a station license and then the operator license. So if you are a club station, for instance, I am the station licensee of a club station. That club station has no operator license tied to it because it's a club. So somebody couldn't just walk into the club and use the club call sign if they didn't have a license themselves. So there's really 2 parts to this. If a control operator who is responsible for the station operation is not the station licensee and something goes wrong, the equipment malfunctions, it is the fault of both of them, the one who is responsible for the operation and the one who's responsible for the equipment. Now, my station in my garage, I'm the station licensee and I'm the control operator of my station.
I got a question, Greg. So you're saying that if you have a state license there, you have to have the licensed person also that operates equipment. Like in other words, the one who's the amateur. So in other words, you can't just have a stage license in there without the other guy who is the operator.
Well, you can have it, but the station can't run. So let's say I'm the trustee, which I am, of the Valley Radio Club in Eugene. So I have in my possession a license that says I am the station licensee. I'm the basically the person responsible for that call sign. But because it's a club, there is no control operator. There is no control operator assigned to that station. It has no operating privilege.
Oh,
Now, my station, my call sign, it is a primary station operator license. I'm the primary station operator licensee. I am the station licensee, and I have privileges because it's me personally. I have privileges as N7JI. So if I take my call sign somewhere, I am using my own privileges. If, let's say, there's a club station, W7PXL, which is the station I'm responsible for, somebody without a license, because they have no privileges, could not walk into the station and just operate it. It actually has to be either me operating with that call sign because my privileges translate to it when I'm there, or somebody else who has a license who has walked into the station and is operating it.
okay, I got
And
it.
that's what we do, actually. We have a club station where we have 15 different operators who go in and use it.
Mm-hmm.
We all use the same W7PXL call sign, but it's under the authority of all those different people at different times.
Mm-hmm.
Okay.
So, next
Yeah.
question for you. So it
Yeah.
sounds like you can have a radio set up and not be licensed, but you cannot operate it. Only a person that is licensed can operate it.
Correct.
You can listen.
Right. Right. Listening is fine, but transmitting a signal, basically the license is a license to transmit a signal. So, yes, exactly. A pile of equipment is a station. A pile of equipment with no control operator can't transmit anything. Not legally. If a repeater, which is automatic, inadvertently retransmits communications that violate the rules, the control operator of the originating station is responsible. So I am actually the control operator of the Valley Radio Club repeater. If somebody gets on the repeater and starts playing music and cursing, that is not my fault. Now, I will try, if somebody tells me, to shut it down using a back channel to kill the repeater. But ultimately, it's the person who is originating those offending signals that's responsible for it and is violating FCC rules and could get the fine, not me. What determines the transmitting frequency privileges of an amateur station? Okay, so let's say we have a club station. Somebody walks in. I'm the trustee. I have an extra class license. Somebody walks in with a technician class license. Can they operate as an extra? Yes or no?
No.
No.
Nope. Nope. It is the control operator's privileges that go along with it. Okay. Excuse me. So a technician class licensee can be the control operator of a station, but cannot operate outside of their privileges. Who may be the control operator of a station communicating through an amateur satellite or space station? That's anyone who's able to transmit on the uplink. Even if your signal is moved to some place where you don't have privileges, you didn't do that. So you might appear somewhere else as a technician. You might appear in a general class band if somebody moved your signal there, but you're not responsible for that. Control point is the point from which the control operator function is performed. If you're local, this is local control. I'm holding my finger on the push to talk button. You can also be automatic control, in which case it's handled automatically. Now, there's also something called remote control. Remote control is operating a station over the internet where somebody sitting at a computer is responsible for indirectly maneuvering the buttons and knobs and things like that. If that person walks away from their remote computer and the station is still transmitting. Is that legal or not? What do you think?
Illegal.
It is not legal. That's right. It's illegal. Because there always has to be somebody responsible for what's happening. That person is the control operator. They always have to be there. Automatic control is a repeater. Basically, whatever it hears, it retransmits. That's automatic. Okay. By the way, we're almost done, everybody. So thank you for your patience. When are you required to transmit your call sign? At least every 10 minutes and at the end. The only time you can transmit without an identification is when using a model craft. You're allowed to transmit at 1 watt on typically 6 meters. And that allows you to transmit controls to, let's say, a remote controlled aircraft. When you're identifying in a band, you use English. You can have a conversation in another language, but when you're identifying your station, you have to use English. You're also allowed to identify a station using Morse code, which is CW, or continuous wave. Why do we use phonetics? They're international, so everybody everywhere knows them, and it eliminates ambiguity. So it's encouraged for us to use them. So if we're using tactical call signs, let's say we're responsible for a road race, and I'm at aid station 1, I can call myself aid station 1. How often do I have to use my official real FCC call sign?
10 minutes.
Every 10 minutes and?
At the beginning and the end.
At the end. Not at the beginning, but at the end.
That's right.
Every 10 minutes and at the end, unless you're in Canada, in which case the rules are different. I can also, if I am in a different place, these are called self-assigned indicators. The words stroke, slant, and slash. So let's say I'm N7JI stroke 6. That would mean I'm in California. N7JI stroke Victor Echo 3. I'm in Ontario. Those are self-assigned indicators. N7JI stroke Whiskey 4. Actually, if you go to Canada, you have to do it. But like if I go to Hawaii, there's no rule that says that I have to sign N7JI/KH6, but you want people to know where you are, so you do. Third-party communications. So let us say that we are having a conversation over the air, and I am at the museum where I do a lot of volunteering, and somebody else is at another museum, and we want 2 kids to talk together. We are both in the United States. Within the United States, we are allowed to do third-party communications where we are either passing information on behalf of somebody else or allowing them to speak it themselves using our call signs and using our privileges. So I am, for instance, I'm standing right next to a 9-year-old who is speaking on the radio, and I am responsible for everything that comes out of their mouth and goes over the air. I am the first party. They are the third party to that communication. That is perfectly legal in the United States. If you're talking about doing it internationally, you have to verify that the United States has a third party agreement with that other country. And believe it or not, there are a lot of countries with which we don't have that. The main reason being that the telecom companies used to consider ham radio to be a threat to their income. And therefore, because it was a threat to their income, because it would circumvent long distance charges, the government itself, in many cases, owned the long distance company. So they didn't allow people to do that. And finally, if the FCC knocks on your door and they want to see your equipment, you have to let them in. You're licensed. You can't say, oh, come back tomorrow. You can't do that. If they're knocking on your door, there's probably a reason. They think there's interference somewhere, and it's probably coming from you because they tracked it down and they want to see it. You got to let them in. This is very, very, very rare, and will almost guaranteed to never happen to you unless you do something really egregious. So,
hey, Scott, the one
Yep.
thing that we didn't talk about was if you're on a cruise ship,
Mm-hmm.
you have to get the captain's approval before you transmit?
Well, you do. I mean, basically, if it's a U.S. flagged ship,
Which
then,
there are only one cruise ship.
well, yeah. Well, but I mean, any vessel. If it's a U.S. flagged vessel, then your license is valid, but you can't transmit on the ship unless you have the captain's approval, because the captain is responsible for everything that happens on the boat. So now here's another question. Let's say that you are, let's say that you're on a Norwegian Cruise Line ship. Could you operate from that? Yes or no?
Not unless you have a Norwegian license.
Actually, that's only partially true. The US and most of Europe participate in something called CEPT, which is the Council of Europe, or what is it, Commission of European Posts and Telecommunications?
It's reciprocity, right?
It's reciprocity, and the United States is a party to that reciprocity. So any member nation in Europe, they can participate and operate in any country in Europe, and the United States is a party to that, so long as you print out the appropriate documents. So when I went to Europe, all I had to do was print out the documents and carry them with me, and I could just start operating when I got there. So I got to operate in Austria. I got to operate in Finland. I got to operate. I don't remember if I operated in Germany or not. I don't think I did.
But what do you mean by printed by documents? You mean register?
No,
I don't know.
There's literally just a piece of paper that you go on the web and print out. And you print it out in French, English, and German and carry it with you.
Oh.
And says it's like TR 601 or something. And it just basically spells out the rules. You look at the rules and you carry it with you along with your license.
Wow.
And that gives you instant reciprocity in those countries. So if you were on a Norwegian Cruise Line ship that's flagged in Norway, I believe Norway is a party to the CEPT reciprocity. You'd still have to ask the captain, but because that's Norwegian territory at that point, the cruise ship is part of Norway, then if the captain says, okay, then you could sign whatever your call sign / maritime mobile, or MM.
Now, if you're on a military base, though, that's U.S. sovereign territory overseas.
Right. And
okay, yeah, go ahead.
And but you would still, depending on what country you're in, you'd be able to use your call sign, but you'd still want to, indicate that you were physically in another place. Otherwise it would be confusing.
Okay, hey Scott, I don't want to go backward, but I'll real minute quick. When I said yes at no time as well, number T1E06, it said a technician license, beat control operator station, operate a amateur extra class band. So in other words, because it's a technician license, the amateur extra band is above, right? It's higher, right?
It's more, it's a bigger range of privileges.
Okay, that's what it was. That's why I had no time. See, I
So-
didn't see that part. Okay.
So
I want to make sure that's what I want to make sure. They went fast on that one.
So the amateur extra, these are these yellow swaths down here.
Oh, I see.
So for the most part, a technician has very, very few privileges on HF, which is why we always recommend that people continue to upgrade, because this is where all the fun happens. So
Okay, now I got it. Thanks.
Other questions? A lot of stuff, but we did it.
Yeah, we
Good
did.
job, everybody.
Too bad we don't get that chart during the test.
You don't need it.
Band.
You don't need it.
Oh, so I'm just trying to memorize. I mean, I know there's more because I've seen them in the test questions, but UHF, HF,
Write it down.
UHF.
Write it
I
down.
got those in my head.
Yep.
Scott, speaking of upgrading, are you
Uh-huh.
going to be teaching another class in the near future?
It depends on time. As it is, my phone already rang today, and I'm going to have to call my boss because I'm on vacation, but he's off in the field somewhere. And he left a voicemail for me a few minutes ago. So
Now, is there anything that you are allowed to bring with you while you're testing?
Nope.
Okay, so no calculator?
Nope. The 4-button calculator. It's not going to help much.
Okay, that's what I was curious about. So thank
And you're not going to be allowed to have a smartwatch present. You're not going to be allowed to have a smartphone present. except as a camera. All right, 3 to 30 megahertz. What do we call that?
HF.
HF. 300 to 300, 30 to 300.
VHF.
VHF.
Okay, and 300 to 3000.
UHF.
Okay, so here's an interesting thing. So does everyone remember channels 2 to 6 on TV and channel 7 to 13? And
Yeah,
channels
that's what I was just gonna ask
14
about.
to
'Cause
83. Okay, this was called VHF, right? This was also called VHF. Well, if you go 2, 3, 4, 5, 6, 7, 8, 9, etc., you'd think that they were right next to each other, right? This is UHF. Channel 2 was at 54 megahertz, which is why 6 meters would wipe out all your TV stations in your neighborhood. The 6 meters is at 50. So channel 3 was at 60, channel 4 was at 66, channel 5 was at 72, channel 6 was at 78. They're 6 megahertz wide, which we actually covered, right? Okay, so we have channel 2, 3, 4, 5, and 6. Okay, channel 7 is at 174. 180. 186, 192, 198, 204, and 210.
Are
Anybody
you talking
see?
about the video or the audio carrier?
That's all the same. They're all
Okay.
The video carrier was AM, the audio carrier is FM, but the whole signal 6 megahertz wide. Does anybody notice what happens in between here? Between 78 and 174 megahertz?
Big a jump.
Yeah, it's a really big jump. So this was known as VHF low, and this was known as VHF high. Now, how about as far as antenna sizes? These are totally different antennas, aren't they?
Mm-hmm.
Yeah. You ever wonder why your TV antennas look the way they did, which look like this?
Different elements for different frequencies.
Different elements for different frequencies. This is actually a special kind of antenna known as a log periodic. It's low gain, but very wide band, because all those different frequencies have different wavelengths. So you would have a many element antenna, and you'd have the really small ones. These are for UHF, and this would be for VHF low, and these would be for VHF high.
I left mine up on the roof. I still have it.
Yep. And you also probably noticed that every element is driven at it kind of has something like this in between them. If you look closely.
I still use it to get locally broadcast stations.
Yeah, but you'll notice that in between the elements you have something that looks like that.
Right.
Yeah, and it's not a Yagi, it's a log periodic. And it's designed so that only two elements are active at any given frequency. The other ones are kind of like out of the range where they do anything. So it's like an automatic band switching antenna.
Us old timers who used to be around, there used to be UHF all the way up to channel 83, and 70 to 83 is gone now.
Yeah, it is. Been
So
repurposed.
here's a practical question.
Uh-huh.
All right, so we go through this, learn a bunch of detail, we get past the test, we got a license, we go out and buy some equipment.
Yep.
Is there a resource out there to help us learn how to use the equipment? Because I saw a guy on Marketplace selling his radio, said, oh, I bought this radio and I could never figure out how to use it.
Join a club in your area.
Here we go. Yep, I'm going to bring this up right now.
I'm going to look at that.
Here
I
we
hope
go.
there's one around here. I'm pretty remote.
There's also a lot of good videos on YouTube specific to the model of radio that you have.
Okay, that helps. Yeah.
Okay, so where are you located? See this thing?
I'm in Central Washington, up north in Okanagan County. Okanagan.
Oh, that's beautiful up there. Beautiful up there. Yeah, give me a zip code.
98855.
Okay, let's see. Let's see what it brings up. I wonder if any of them are going to be in BC.
Possible,
Okanagan County Amateur Radio Club.
There you go, Okanagan, Washington.
And it's a small club. It says six members, but let's see if they've got an active website. they've got somebody who's responsible for it. And it's not going to come up. Well, shoot.
6
They
members
don't have a
means high
club in your
quality.
area. If they
Hmm?
don't have a club in your area, join your Coast Guard auxiliary and you can use their radio room.
Possibly.
Well, I'm not anywhere near the coast.
Yeah.
There's Coast Guard auxiliary at the lakes, not just at the coast.
Okay. Check.
Let's see. Okanagan County Amateur Radio. Let's see. Well, let's see if they have a present. Oh, look, well, they do have some present. They exist.
When was their last? What would you looked at on Facebook?
March 24th.
Okay. I
So
can look them up.
Oh, okay. And also, they are not that far from the Spokane DX Association, and I know Spokane DX Association as well. So, yes, you are not without hope.
Yeah, I can look them. I'll check.
So, yeah, I mean the clubs are your, really your lifeline.
Yeah.
It's really important to join a local club because this is it's a collective knowledge thing. And, I realize that there are some places where the clubs are really, really small or not, or almost non-existent. And there are a lot, I belong to, I don't know, 10 or 12 Facebook groups. And any reasonable question that I get and any reasonable question that I see, I try to answer.
And I'm assuming that a metal roof on your house is not a good thing.
Depends.
Unless you tap into it.
That's right. Yeah. If that becomes a ground plane, that could be a great thing.
Mm-hmm.
Jessica, you had your hand up.
Yeah, sorry. You kind of answered it, but just to clarify, so my local club, it looks like their last little get together session / testing session was in 2018. So would Facebook be the second place you would go?
Well, it depends. Where are you?
78504.
78504. Let's see. Let's see what this says. Let me share this again. Find a club. 785. Search for ARR affiliated club. Make sure everything else is unselected. 78504. No clubs to display. Oh boy. Okay. Well, where exactly is that? That like Nebraska?
I am at the very bottom tip of Texas, a rock's throw from Mexico.
78504.
There's a South Texas club, but it's like people consider South Texas to be like Austin, and that's like 6 hours from me.
Yeah. When you say at the very south tip, let's see, Texas.
There is a club in San Antonio that's pretty good. I know it's a little bit of a hike, but it might work out.
That is 4 hours away.
Yeah.
Are you in Brownsville?
What's that?
Are you in Brownville?
I am about an hour from Brownsville. I'm in McAllen.
Oh, McAllen. I know McAllen. Yeah, right across the border, actually. Yeah. Yeah.
There have to be some. Okay.
Yeah, those are the guys that last got together in 2018.
Oh, I got to go through this, huh? All right, fine. I'll bite. See if I can do it right. I am not a robot. Okay.
They have a calendar, and that's where it says the 2018 stuff.
Yeah, it just might be that it hasn't been updated, but that's why it's important for clubs to, and it says they're ARRL affiliated. Let's see, ND5N.
Thank you, by the way. I appreciate
Yeah.
it.
Let's see. We're gonna look up South.
Because I had the
Texas.
same question. I was like, I know I will ace this test, but functionally,
Mhm.
could use some pointers.
Let's see.
Wish I
South
had your
Texas.
gift for taking tests.
Practice, practice, practice.
I did like 6 hours of studying last night, and took the practice test like 25 times.
Okay.
I'm trying to do it in under 7 minutes.
Oh, you're gonna do that. Okay. The fastest I've ever seen is
Trying to
7
beat
minutes.
the record.
Yeah.
My personal record at this point is 91% in 3 minutes and 59 seconds. So I'm gonna try to beat that tomorrow.
Okay.
Learning
So,
disabilities do not make fast testers.
okay, let's see. Baytown, Beaumont. I see the problem is that South Texas includes Houston. So
Yeah, and that's 6.5 hours north.
right. No, that
It's
doesn't help.
kind of funny.
Yeah. What would be really good if there was if there was a map. I wonder if
There are Coast Guard folks here because I'm about an hour and change from the coast.
When I was talking about the Coast Guard, not necessarily, I'm not talking about the US Coast Guard, I'm talking about the US Coast Guard
Oh.
auxiliary. The auxiliary.
Boo.
So all the lakes have an auxiliary unit, just about. And they patrol the lakes and keep people safe, and they help with drownings, and they assist the Coast Guard if the Coast Guard needs something. But the reason I brought it up is that usually they have their own radio station.
Yeah.
And if you get your ticket, then you can, and you join the Coast Guard auxiliary, then you can hang out in the radio room with them and, talk back and forth between the guys out on patrol.
Oh,
and
wait. So how far are you from Corpus Christi?
I'm far, but I'm not far from South Padre Island.
Oh, okay. Ham radio.
You must see the
South
SpaceX
Texas
launches.
ARC.
That's a walk over the bridge from Matamoros.
Yes. Yep. 75 cents, and I can get a lot of things cheaper than I can in this country.
Yeah.
75 cents down across?
Something like that.
Okay,
It's
well,
been a
here's
long time since I've been across.
Here's the South Texas ARC. That's in Corpus Christi.
Yeah, that's about 4.5, 5 hours.
Is it that far?
Yeah, it's pretty far.
Texas is big, man.
Oh, I know.
You can
I mean,
drive for
It's like a
11
whole
hours and
country.
never leave
oh,
the
I
state.
know. I work in Texas a lot. And
All right, I'm checking out. Hope to check in with your club, Scott.
Indeed. And
all right. Thanks so much.
Thanks, you guys. I'm still looking here. Let's see. Harlingen.
That's not that far from me.
Yeah, South Padre. Let's look up South Padre. Coastal Bend. Don't know what that is. Let's see what Coastal Bend is. Ingleside, Texas?
No idea where that is.
San Patricio County.
Ingleside's the other side of Corpus Christi.
Yeah, okay. Well, there's got to be something.
There was a group Facebook punched into the chat. I need call sign letters to answer the questions, but I'll check that out once after the test.
Well, I wonder if there's a what's on the Mexico side.
Ruidoso Downs.
Well, there's Matamoros, Reynosa.
By Reynosa, but it's not a place I would really love to
Oh yeah,
go.
yeah. How about Brownsville? How about Brownsville?
Yeah, that's like, depends on the day. It could be 35 minutes, could be an hour, but it's not that far.
Matamoros, they closed the drive-in restaurant, didn't they?
I am not sure.
Yeah, that was a very old restaurant. We used to go across the border to eat there.
Well, here you go,
That's
Brownsville.
awesome. Oh, sweet. And they look active?
Let's see, main page. Well, it says they're
Oh,
ALRL
Charo. So
affiliate.
they probably go over the border because a lot of the Charo stuff's with Mexico and US. So that's cool.
W5CRC. Let's see if they have a QRZ page. Communications Hobby Amateur Radio Relay Org. 5YE. So they do have at least something. Local links. Upcoming events. Let's see if it's up there. 2019.
There's a military academy in Harlingen called Marine Military Academy. They might have a club.
Well,
that would be cool.
You know, I would see what their status is. Some clubs are really bad about updating their sites.
Harlingen also has there's a group out there that fly all the old World War II aircraft. They might have something going on too, those guys.
Yeah, there's a ton of like military here, which I know, wouldn't necessarily mean that they are involved in this, but I feel like there's got to be some people in that group.
The Commemorative Air Force is who he's thinking of.
Right. It used to be the
Confederate Air
Force. And they changed the name. Yeah.
Yep.
Which it's a civilian organization, has nothing to do with the military. That is a bunch of pilots that had World War II aircraft that they keep up. And
let's see, calendar.
The last two B-29s.
Okay, so where's this one? Rio ARC.
San Benito, it says. They meet at the main hall.
They meet in the Harlingen Irrigation District building.
Sweet. That's not super far.
K5RGV. That's the Rio ARC.
Okay, cool. I'm gonna make a note of that.
Have, oh, and these are up, and this is updated recently. Every Wednesday breakfast, every Saturday breakfast. West side of Harlingen. That's on your side.
Oh, yay, awesome. Awesome. Badass. Thank you so much. I appreciate you. And thanks to everybody else who had some tips and tricks to help us navigate this. I appreciate y'all too.
W5RGV or K5RGV? K5RGV.
Got him.
Nope, W5RGV.
Thank you.
Mm-hmm. See, it's different from this one. Oh wait, it is K5RGV. K5RGV. Rio Amateur Radio Club. Oh, Jim Duffy. That name sounds really familiar. I mean, really familiar.
Should I name drop you if I meet him?
No, it's been a while.
No, Scott owes him money. Don't mention his name.
I don't, but I thought he lived in New Mexico. And I don't think it's EY. I think it's Y. So, but yeah, there you go. K5RGV.
Thank you.
Anything else? I'm gonna hit stop before I forget.